Also, yeah, I have to lift this mic. Testing, testing. Hi, everyone. Hi, hi. Yeah, I'll take this mic, actually. Thank you for coming to this early morning talk. It's going to be a talk on formal verification and like some basic methods in distributed systems and reasoning about faulty distributed systems. Everything presented here has been formally verified by the team at Runtime Verification and is like available to like click and check, and you can look at the proofs in Coq. But this talk is not going to be focused on the proofs, more just definitions and theorems, and not really walking through the proofs. But you can check them out. And there's a So I've separated in a bunch of sections, a section on validation theory, a section on equivocation theory, and then on relating and reducing Byzantine faults to equivocation faults in context of validators. So let's kick it off. So let's talk about validation. And this, so here's these slides were actually a little disordered. This is the name of the paper, validating labeled state transition message production systems. So it's for modeling distributed systems, faulty distributed systems, and all these amazing people worked on it for a long time. Here you can scan this QR code and pull up the PDF if you like. I'll show this also again later. So here's the validation theory section outline. Basically, we're going to go through the definition of this model, its compositions, and then the definition of validator. And then we'll move on to the equivocation section. So here's the first definition here. So a VLSM is a tuple, as we often like to define these things. It's sort of like a state transition system like you're normally used to, except for it has a few other things, like a label, which is also not too unconventional, and but it has a first order message set in the definition. It has initial states and initial messages, and then there's a transition function that takes labeled states and messages, optional messages, and gives us states and optional messages. This is like the state transition / message receipt and production function that like describes, for a particular VLSM, sort of what's happening computationally, you could imagine. And then they're also equipped with another thing, which is why they're called validating, this beta, which is a validity condition. And it basically says when it's going to be valid to transition on a label from a state given a message. So when you're in a particular state and you receive a message and you might want to transition, there might be multiple possible transitions, each identified by a label. And some of them might be basically banned. Even though they're defined by the transition, the validity condition won't let you take that transition. So this is like a state transition system with native messages, with initial states and messages, and with a like a transition function that's totally defined over this domain, and then we sort of restrict it, effectively making it partial with this validity condition. This is like the validation condition. Basically, we're going to imagine that these things don't transition, even though the transition is defined when the validation condition is not satisfied. And so that's the definition, but actually, I haven't told you sort of how to get the states and messages, but it's sort of what you would expect. You start at the initial states and the initial messages, and then we build up this fixed point by taking the union of all the states that you get from the transitions and all the messages that you get from the transitions, and transitioning from those states using those messages. So basically starting from the initial states and messages, transitioning and sending all the messages that are produced from there, and receiving them, and doing it over and over again, basically until you even get stuff like a node in an early state receiving a message from some other state. This really is like a big fixed point. And so there is an interesting thing that can sort of happen, which is the validity condition can be satisfied even when an input message is invalid. So we have to slightly distinguish between just the validity condition being satisfied and the actual trace being valid. The trace is valid only if all the input messages are also valid. So no garbage in sort of allowed in a valid message. So that's basically the definition of VLSM, and then they have a pretty natural way to compose them. And so now I'm going to go through that definition. Unless someone has like a question now before the composition. Okay. So basically what we're going to do is we're going to take a disjoint sum of the components for the label. So we identify the label, which component it is. The state is a tuple of the component states. The initial states is a tuple of the initial states. And then we have like a union of the messages for the initial messages. And then here actually we're composing VLSMs that have the same message type. This is just so that all their transitions are defined and everything, and to let them send messages to and from each other, so they're not just independently. Like if that was a disjoint union, they wouldn't be communicating. So we have a disjoint union for the labels, tuple for the state, and then a regular union for the messages. And then in the free composition, we have a transition that basically just affects only one component, exactly according to the transition that would have had before the composition, and checks the validity condition only of that component exactly like it was before. So very little, basically nothing being done by the composition except for transitioning the individual components and checking their individual composition, their individual validity conditions individually. There's no composition-wise constraints, but they can message each other in this thing. And then note also that this is also a VLSM, and that's why it's like sort of it's a composable model. Same tuple definition and everything. Yeah.
So the split up of the transition functions and the validity criteria.
Mm-hmm. So the question is the split up between the transition and the validity purely mathematical? I mean, I guess it's for the sake of convenience when dealing with the math end. But I mean, in more traditionally in math, you'd use like a partial function, I guess. Whereas here, we're about to get into this conversation about validation and distributed systems and what can happen in a distributed systems that you might not be able to tell locally about, and so it gets there is a reason why we are thinking about the validation at different levels, and actually and that actually it does sort of spell it out. Basically, there's going to be actually the next slide. We're going to talk about constrained compositions where there's an additional constraint on the so basically like this constrained composition just basically conjuncts a constraint on top of the validity constraint of the free composition, which just is the individual constraints applied independently. So this composition constraint lets us sort of analyze things a little bit more conveniently than just a partial function approach. Yeah, so the question is if we're doing this to try to see if a transaction is possible but not valid. And yeah, you're very much going in the right direction. And we're getting there with this definition here. So This is the definition of validator. It's a very natural, simple definition of validator, which is kind of useful in many different contexts. So so the components are a validator for the composition. Basically, they're checking if they're truly a part of that composition, or if they're like, and they're sort of, only transitioning as if they are part of that composition, even though they don't know it per se. So let me just go through this definition. So basically, a component in a constrained composition is a validator if any transition that component can make can be lifted to a valid transition in that composition. So if the component has a valid transition, then if a validator has a transition, which it can take, then there's also a transition in the composite system where that validator can take that transition. It sounds weird, but basically it's not. The local condition lifts to a distributed one. And so basically this local component is checking about a condition that's distributed across the whole composition. And that's sort of non-trivial because of information disparity between the nodes. So there's a message here being received, and this is the message being sent, and this is the label, and this is a constrained transition, which doesn't necessarily mean that M is valid. However, it's lifted to a valid condition, transition with M being received. So basically the validity condition of the component is enough to guarantee the validity of the message received in the composition. So basically the component locally is able to verify whether the message has this distributed property. And that's why it's called a validator, because it's basically able to check something that's outside of its scope. And it's again defined here with respect to a particular composition and a particular constraint on that composition. So you might have different validators for lots of different distributed settings. But we're specifically going to be interested and focused on equivocation for a reason that I've already talked about, but sort of reveals at the end why equivocation is so particularly interesting to look at. So the equivocation theory section, talk about evidence, and then using evidence to describe composition constraints that limit and validity conditions that limit equivocation. And then we'll talk about models of equivocation, and then all this will tie in nicely when we start talking about Byzantine faults. So this is sort of what we're used to seeing in blockchains when it comes to slashing conditions. This is a starting point, or was a starting point in our proof of stake research. Basically, when messages have the same sender, they're like collected by the same node, or like in the same smart contract, you can imagine, and they basically could not have possibly been produced by the sender in a single round of the protocol. So if you run a trace of these things, there isn't a single trace where those two messages are produced by that node. And so this is evidence of equivocation. This is somehow, we have two messages that couldn't have been produced by their sender. And we have them sort of in the same state. This is sort of a faulty behavior. And this is local evidence. And here's an interesting definition. Yeah, of course. Sorry, if we don't have a history, how do we check that what? Yes, so so that's a good question. I mean, it's I think it's undecidable in general, but the question is whether it could not have been possibly produced by. So basically, you need to sort of quantify over all traces and say there is no trace where these two messages can be produced. So in practice, we're going to have lots of simplifying assumptions, like you're guessing, but the definition doesn't say how, how we can come to this decision about whether a message could have been produced. It's okay. That's actually another nice thing about having the validity conditions as sort of like predicates. You can have undecidable conditions, whereas if you were using partial functions, that would be an issue. So there's global evidence is a little bit more interesting and a little bit more maybe a little more decidable, right? Because in this we have like a sort of global view of the trace. So we can basically check that the message was not observed. So. Yeah. So this is getting into some later content that I was hoping to. I think I've slightly misordered this. But anyways, if you have a God's eye view of a VLSM trace, and you have a message that wasn't sent by a component, but it was received by some component, that's an equivocation. Sorry, Denisa, could you go ahead? No. Mm-hmm. Yeah. So here's a theorem, right? That the local equivocation is always going to be less than the global equivocation. And all these are checked in the theorem provers, but you can sort of imagine why that is. And basically, we can use these global and local definitions of equivocations to limit the equivocations to create basically a composition constraint where the faults are limited. We can easily just say, okay, well, there shouldn't be any equivocation, and talk about DSM traces where there aren't any equivocations. And we also use the full node assumption to reduce the amount of equivocations, because then you can only sort of get an equivocation from the sender of a message because you've already received all of its dependencies. We can limit equivocations to just a subset, and we can also assign weights to the nodes and then limit the equivocations by their total weight. And these are like example conditions in composition constraints, or a local constraint. So this is a composition constraint for a validator on a global constraint that looks like this. And so like in this particular example, this validator is just checking the local equivocation weight, and if it's less than t, and the composition constraint is checking the global equivocation. And the validator property is basically that from the local one, there should be a state where the global one is also satisfied. Basically, the lifting property of the valid state from the local to the distributed property. So, this was talking about basically what equivocation looks like and how to detect it, and therefore how to talk about non-constructively traces that have limited equivocation. But we do have a very nice constructive sort of approach to where we can describe equivocators, and basically there's two models for equivocation. There's a state equivocator, which basically splits its current state up or has many states for the same validator, and it can do that by forking or by starting new machines. And it also has, and there's also the message equivocation model, where instead of the state splitting and having multiple copies of a validator, validators can receive messages that haven't been sent. And sort of this sort of is what we're observing in that definition of global equivocation. And it turns out that these two things are equivalent, actually. The traces that you can get from the state equivocations and the message equivocations are the same. Whether you are like receiving messages that haven't been sent or splitting up states, if you like project down to those equivocator states, we get exactly the same traces. And it's kind of interesting, basically like splitting a timeline and communicating across timelines end up producing exactly the same states. And so these two are models of the same phenomenon, equivocation. And that's why we have those two definitions there, where one of them seems a little bit different than the other. You know, somehow two messages that couldn't have been produced in a single trace evokes a state equivocation, and a message that hasn't been sent yet being received evokes the message equivocation. But they are equivalent. They are equivalent. So that's a pretty cool result that's going to be useful later. But basically, to repeat it, the models of equivocation that split the state and models of equivocation that allow communication from other traces lead to the same traces for validators for a limited equivocation. So that means that when you have evidence of equivocation being produced, you know, you can produce that that evidence either with state equivocation or message equivocation, and you get exactly the same state, exactly the same evidence. Great. So that's the first two sections. Any questions before the next one? Excuse me. So here we go. Yeah, please. Your microphone's off. Sorry. You try it.
Okay. I guess in the previous discussion, you kind of assumed finite branching, which means that you cannot make infinitely many copies at the same time.
No, we have unbounded. We have like a list, like unbounded list of copies.
Okay, but still finite, right?
Yeah, finite, but finite unbounded. Yeah.
Because when it comes to infinite messages and states, I was like.
That's a good question. I think we have possibly infinite traces, but not states and messages at the moment.
Yeah, I guess so.
Sorry about that.
Yeah.
We'll get there. Yeah. So now basically we're going to do. Yeah. Go ahead. Sorry. Yeah. Please use the mic. Yeah. Microphone. Just close. Just hold it closer. Oh no, never mind. Sorry.
Hi, can you hear me?
Yeah, that's great.
This is weird. Sorry. I think the states can be infinite, but not reachable. It's a matter of which are the reachable states. But it matters how many labels you have, and that gives you how many moves you can do. But in reality, yes, it's bounded and yeah.
Great. So let's move to the Byzantine faults. So basically, we can model Byzantine faults in VLSM by replacing a node with a node that basically has a free behavior that uses labels to send and receive any message at any time. The important behavior is that it can send any message at any time. Basically, modeling someone that can send any sort of malformed and invalid message at any point. And we do have a little bit of constraints, which is that we don't let them forge messages on other nodes, and we do have a full node assumption. they can send any message, signed by them, from them, basically, without forged messages inside. And so we can replace equivocation limited validators with Byzantine components and find that they have exactly the same traces. The ones that aren't replaced have the same traces. So if you have a trace in the equivocation limited composition where like some set B of validators is Byzantine, they have the same traces as if they're composed with equivocators instead. And basically that's because of the validator property. So if you have a validator property on receiving a message from a Byzantine center, that means that there is a composite state where that sender, as an equivocator, can validly send that message. Because here we're validating for a limited equivocation setting, so some amount of equivocation is valid in that setting. And so we can replace these Byzantine nodes with equivocating nodes, and then look at the traces of the validators that aren't equivocating and show that they have exactly the same traces. Denise, do you have a question? Okay. And the same result also holds for weight-limited equivocation model. So it's not just for a fixed set, but for under T-limited equivocation weight. All the behaviors of non-equivocating components due to equivocating components is exactly replicated by Byzantine behavior with the same T limit. And so that basically means that under the limited less than T weight equivocation, we get all of the same traces for the validators as limited less than T weight Byzantine vaults. So that's sort of the sort of magical way that we can not use Byzantine fault tolerance. Basically, for these equivocation limited validators, equivocation faults are exactly as expressive as Byzantine faults, because by validating for that limited faulty setting, they're restricting their transitions a lot. And if a Byzantine node can send some malformed message that they receive, that means that that transition can be lifted to a valid state in the composition under the limited T equivocation condition, which means that there are nodes in the composition distributed that satisfy that less than T threshold, but aren't Byzantine nodes, but equivocation nodes. And then putting those transitions together to get traces, we can rebuild exactly the same traces. And so basically this forms an alternative for analyzing faulty distributed systems to Byzantine fault tolerance. And quite simply, by studying equivocation limiting instead of and equivocation faults instead of Byzantine faults. So somehow equivocation faults are like a special kind of fault where if you validate for limiting equivocation, that's just as good as validating for limited Byzantine faults. Oh, sorry, that's just as good as that actually lets you throw out Byzantine fault tolerance analysis altogether when thinking about like what traces you could go to. You can sort of just go to the protocol defined ones, and it doesn't really matter what the Byzantine nodes do. They're basically just protocol following equivocators as far as the analyst is concerned. And so instead of having misbehaving nodes, they just have either like a state replicator or a message passer that sort of crosses timelines, which is sort of much more tamed types and well-defined behavior. So later we're going to relax the full node assumption and treat synchronization faults. I'm out of time. Thank you so much. Thanks for coming. Really appreciate it. If you have any questions, you can find me outside later. Thank you.
Hey, good morning, everyone. Thank you for coming to our workshop today. Before we start, if you have any questions, just throw your hand up. It'll be pretty relaxed, so yeah. Let's just look into the workshop overview. Introduction, that's us right now. We're going to go into Zatu Genesis, see sort of how it happened, why it happened, and then we'll look into the data sets that have emerged since. We'll then progress into how we're using the data, how others are using the data. Leo over here will then present, he's from the Mega Labs team. He'll present the big blocks test that happened last year. And then we'll have a live tutorial from Tony. He'll go through how he uses PyZatu to run his analysis. Sweet. So a little intro on who we are. I'm Sam. That's Andrew. He's hiding. We've both been doing DevOps on the PandaOps team for the last few years. And we both have a deep appreciation for things like Ethereum and observability. As for our team, ETH PandaOps, we started out in 2021, being thrown straight into the deep end with the merge. We're embedded in the F and do DevOps for the protocol. And we post blogs semi-frequently on our website. We try to keep them really high signal. They're the best way to keep up to date with us. Scan the QR code, and it'll jump you straight there. Our team has a pretty wide range of projects cooking at all times. You've probably come across a couple of them. For example, if you've ever run a node, you've probably checkpoint synced from an endpoint that was running checkpoint Z. You may have also seen Parry and Barnabas whipping core devs in the core dev calls. Yeah, there's a lot of stuff going on. So let's move on to the workshop. To set the scene, it's late 2022 and the merge has just happened. We've switched from proof of work to proof of stake, but in doing so, our consensus mechanism has become a lot more sensitive to time. Suddenly, the when of things happening has become a lot more important. And this data at a global and network level doesn't really exist. It's easy to check that a block was seen, but it's much harder to see when that block was actually seen in Sydney compared to Berlin, for example. And now that we're clear from the merge, researchers start hacking away. They want to upgrade the beacon chain, but yeah, they need this timing data to validate their ideas. And they start capturing it themselves. Varying scales, different implementations, it's hard to expose, it's hard to validate. There's a bit of potential errors in there. So we started to brainstorm ideas on how to solve our problems. We needed to somehow integrate with existing beacon node implementations, as neither of us were really too keen to implement a full beacon node. As DevOps engineers, we'd usually just implement a few Prometheus metrics, put the feed up, and call it a day. But millisecond level precision is pretty important, so that rules out Prometheus metrics. Log aggregation was also another option, but it's definitely a moving target. These things change all the time. It's not really something that the client devs really pay too much attention to, and we'd also just have to turn on debug level logging. We'd be throwing the kitchen sink at our log aggregation pipeline, and it would potentially be an unreliable result anyway. So that rules out logs. So we started to look at other options. Turns out that the Beacon API has this thing called the event stream. You can subscribe to it, and when the Beacon node sees things or does things, it will emit an event. So blocks, attestations, voluntary exits, everything. It was all there. The beautiful thing is that the Beacon node implementation all supported this endpoint in a standardized fashion. So what we landed on was Zatu. We used Go, gRPC, and we thought that it would be responsible for just collecting Ethereum timing data. It definitely wasn't going to be trying to store or query that data, but the plan was to derive events and ship them somewhere else. To do this, we initially created two modules. Zatu Server would create events from other modules, would collect events from other modules and send them somewhere else, and Zatu Sentry was our first module. It would run as a sidecar next to every beacon node, subscribe to events, and send them off to Zatu Server. We wanted to make sure that all of the events followed the same structure so that it was much easier to add new events into the future. And also, really importantly, since this is like a distributed system, we wanted to make it clear how much you could trust the data. So data coming from a client is not necessarily trusted, but if it's been derived by Zatu's server, something that we control, maybe you can trust it a bit more. This example event is for one of our Zatu Sentry nodes running on mainnet, subscribing to a beacon node, and a new block has just come in. I've redacted a couple of the fields, but yeah, that's the general idea. That's all great, but we still hadn't really solved where to send the data. And it turns out it was a lot of data. Fortunately for us, ClickHouse exists, and it is goated. It allows us to store events at a scale that we didn't really think was possible. In July, we hit 4 commas of attestations in our ClickHouse cluster with just 14 terabytes of disk usage, which is just ridiculous. Given that those attestations, we don't keep the signature because we're getting it past the trusted point. But yeah, still, it's crazy. All right, data sets. I'll hand over to Andrew.
Data sets. So we just started with Beacon API events, and sort of over the last 2 years, we've been trying to collect it all the data, as the project name suggests. There's some overlap between the data sets. For example, the Beacon API event stream and the libp2p datasets sort of collect events at the head of the chain as they're happening. Whereas canonical sort of beacon events and execution events is sort of the finalized data which can be referenced from other data sets. So there's a lot of sort of cross sort of queries that happen. There's also, so the module SAM talk about like the Sentry and the libp2p Sentry. We run lots of them. We collect a lot of the same event from a lot of different regions around the world. And that sort of gives us propagation times, timing data, regional data, sort of what's happening in Europe, what's happening in US, what's happening in Australia. Sort of allows you to sort of differentiate sort of what's happening around the world. We also collect MEV relay data, sort of bids, proposer payloads. We have a sort of discovery module that sort of crawls the execution layer, captures mempool from different regions around the world, and we also capture canonical execution sort of data. We like to use open source projects, a couple here. So Hermes by ProBlab is a sort of lib P2P sentry, I guess you could call it, that you run. Connects directly to the lib P2P sort of gossip sub network, and you can sort of capture that data right off the network. So it's pretty good. And we also use Cryo by Paradigm. It allows us to get the sort of canonical execution data pretty good. We just sort of backfilled all the way to Genesis, basically, and made that public a couple of weeks ago, which is a lot of data. Also, check out Storm from Paradigm talk later today on data sovereignty. Should be good. Also, check out ProBlab's talk yesterday on how they do a lot of work around the peer-to-peer network. It's pretty interesting. Yeah, so we were collecting a lot of data for researchers. We didn't really know what to do with it. There was sort of internal EF researchers and a few researchers outside. So we decided to open source it and sort of put it in Parquet files and make it available to everyone. You can read more there. There's a bit more sort of docs on how to sort of access and read it, but sort of every, some tables will be like per day or per hour, depending on how big they are. So you can grab, for example, block events for that date, and you'll get the sort of raw data in Parquet file. So if you want to do analysis, it's pretty easy to get started. Yeah, a couple of months ago we allowed, so we have a lot of sentries around the world capturing Beacon API event stream data. It's quite costly because you have to run obviously a Beacon node and attach a sentry. We sort of allowed the community, if they want to run the sentry next to their Beacon node. You can opt into sort of what sort of level of geo-IP data you want to send us, whether it's city, country, continent, or none at all. So it's up to you guys, but if you want to sort of contribute, we're open to that as well. It's just good to get data from a wide variety of regions and setups, and it just helps research as well. And all that data we anonymize, so you can, no one can sort of track what Beacon node you're running, anything like that, but we also publish that data, so you can also check it out yourself as well. All right, using the data. This one's pretty interesting. We use SIGP's Block Scout block print tool, which you can check out there. It basically uses machine learning to try and assign a consensus layer client to a validator index. We then use that data, because we've got all this data, we know who's supposed to be attesting, we know who's not attesting, we can then link that to client data, and it gives us pretty quick response time to figure out if there's an issue with a particular consensus client implementation, because you'll see potentially thousands of validators offline for a certain client implementation. So this is really actually useful. We've got other sort of dashboards, Grafana dashboards we use for devnets, testnets, mainnet, around block timings and stuff like that we use internally. But yeah, there's a lot of monitoring goes on sort of about the network, about timing. Just gives us another view of the network. There's also ProBlab, which I mentioned before. So they do some cool work. So they have weekly report that uses Zatu data. It shows block arrival time. I think there's also the size of the block and the distribution there. Check it out. It's pretty cool. Yeah, they're doing great work. After 4844, we had a ESP data challenge, which was basically write a blog post about the blobs upgrade. There was definitely some cool blog posts there. I just picked out one here, which is pretty interesting. But yeah, in the future, there could also be more opportunities for data challenge. Just keep an eye out. Also, there's another one from Evan from, I'm going to butcher that, I don't know if it's Premev or Prime V, but he did a pre and post sort of analysis of 4844, which is pretty cool, using our data. Lastly, some randoms use our data on ETH research, which is cool. So yeah, that's basically it. Thanks for that. I'll pass it on to Leo to talk about his awesome work.
Thank you, Andrew. So good morning, everyone. Thank you for coming to this session. Yeah, I'm Leo from Mika Labs, and by the way, we have a booth in front of Classroom E in case you want to drop by and keep asking questions about what I'm going to present here or something else, the work that we do. So yes, I want to talk a little bit about this research that we did with the SHA-2 data. Just to put you in context, this happened last year in 2023. We have been working with the Ethereum Foundation researchers about data availability sampling. And one of the things that we wanted to know is how much time does it take to disseminate a huge block in the Ethereum network. So we were building a simulator that disseminates huge blocks over the network, and we managed to, after some months of work, to have some idea about how much time does it take to disseminate data of the network. But then we needed to somehow validate these results that we were getting with our simulator, and so we were, scratching our heads on how to do that. And one of the ideas was, okay, how about we pay a huge transaction into a huge block in the Ethereum network, and we, see how much that how much time does it take to propagate over the network. So we kind of artificially injected, and by we I mean the Ethereum Foundation, injected big blocks on the network, and then thanks to the SHA-2, Sentry nodes and SHA-2, we managed to see how much time does it take to propagate. Then a couple of weeks later, I was looking at the data, and we were recording the block sizes for the last kind of 6 months or something like that, and we noticed that there were plenty of big blocks in the network. And then at that moment, I contacted the EF researchers, so I was working with Danny Ryan and Dan Rudd at the time, and I say, hi, you guys are still injecting blocks? And they told me, no, that is over. And I said, well, I am seeing these huge blocks on the network. What is going on? And so this is when we kind of discovered that there is quite a significant number of big blocks that occur naturally, organically in the Ethereum network. And so this figure that you see here is an example of that. So this is 6 months, I think, from April to August 2023. And we are plotting all the blocks that are over 250 kilobytes in this distribution. So please notice that this is a logarithmic scale on the y-axis, right? And then you see that we go to up to over 2 megabytes of size for some blocks. Now, we also found quite weird to see blocks over 2 megabytes, because if you know how the gas system and the cold data works on the blocks, you know that usually you have 30,000 gas to pay, sorry, 30 million. And you have, and then if you want to store 1 byte of data, you have to pay 16 gas. And so if you make the computation, that says that the biggest block in the network should be only 1.8 megabytes. And so we look at that, but in fact, the reality is that if you pay for zeros, then that is for gas. So yes? This is pre-DNF, yeah. So this was last year in 2023. So the question for it was whether this is pre-DNF or after 4844. This was last year, so this is before that. And yeah, so then actually, in reality, you could actually construct a block that is up to 7 megabytes or so. And so because we had all these blocks, then we can actually have a lot of fun and try to analyze how these blocks propagate in the data. And that gives us a lot of information about how much we can increase the number of blobs in the future for data availability sampling and so on. So thanks to SHA-2 and the Sentry nodes that the DevOps guys deploy over the planet, as Andrew was mentioning, you can analyze how things behave in different regions of the world, right? And so we took this set of big blocks, and we try to analyze what is the distribution of arrival in different locations. So one of the things that you can try to analyze is, for example, okay, what is the difference of the blocks arriving between Amsterdam and, for example, Sydney? And you see this more or less like half of a second for this particular case. And you also see that most of the times the block arrives within the 4 seconds, which is great. Otherwise, these things will not work because the slots are 12 seconds. So you need this data to arrive quite fast. That was one type of analysis that you could do. But then the other thing that we were actually really more interested is how blocks arrive according to their size. So we put the blocks in different bins, in different colors, from 0.2 megabytes to 2 megabytes, right? And then we analyze how much time does it take for those blocks, according to their size, to propagate over the network. And this is more or less the distribution that you see. So you see, for example, that there is between 200 kilobytes to 2 megabytes, there is almost like a 2 seconds difference right there for that difference of size in blocks, right? So that is quite interesting because then that gives us information about, okay, what is going to happen when we activate 4844, right, after the Devcon fork. So this was actually really great results because 2 megabytes is actually a lot. Right now we have maximum 6 blobs, which is about 700 something kilobytes. And so we say, okay, that's fine. If we already have 2 megabytes blocks that propagate over the network without any problem, and we didn't even notice it, that means that we can allow for 6 blobs to run over the network, and we should be okay. Okay. And then we deployed Devcon, and we noticed that, yeah, that actually works. And then this kind of data give us information also about how much further we can go in the future, right? Before we implement data sharding or PRDAS or whatever we want to call them. So this is why this kind of data is important for researchers, and this is what why this is important. And another thing that I want to show is, so we created this SHA-2 dashboard. You can access it on the QR code if you want. That give us real-time data on data that we get from SHA-2. So we have a bunch of different things that I'm not gonna go into detail, but I just wanted to mention maybe just a couple of them, and then you can go and look at the details later. Or again, if you want, you can come at the booth and we can discuss about it. So things you can see here. So for example, this is a difference of how the number of blobs looked at the beginning. So this was during the first 3 months of after Devcon was deployed, and this is how it looks today. So at the time, you had like 56% of the blocks with 0 blobs, and today you have like 40%. So the blue color, the blue size here, has reduced significantly from the initial, the first months of Devcon up to today. So this is the last month, just like October. And you have seen that the other colors have increased in size on this pie chart, right? So this has changed. The number of blocks with six blobs keeps more or less constant. So in this case, I think it was 20%. Right now, we are 21%. So that one is more or less constant, but the other ones are increasing in size on this pie chart, while the number of blocks with 0 blobs is decreasing. Tony has also a very nice post that shows how this distribution changes over time, not only for the counts of blobs, but for many other things. So I also advise you to check on that one. And then you can also see in real time the propagation of blobs over the network, right? So you have all these events that Chato is recording, and then you can plot all that for the last month, for example. You can plot all the blocks and all the blobs and see what is the latency of arrival for all the blobs in the network, right? Again, you can access this data on our dashboard, and we also have an API in case you want to play with the data as well. Another thing that you can do is try to look at how much blobs are used. So that means how much data is actually put inside. So when you have a blob and then at the end you have like 50 kilobytes of zeros, then we are assuming that that is not used, right? And so you can look at those details and see what is the usage of the blobs. And so this is how it looks from the last month. So I think they are very fairly good use of the blobs. So that's like almost 90% of the space is being used in the blobs. That was not the case some months ago. It was something around 60%, I think, some time ago. So this is also evolving, as rollups and layer 2s get more familiar with how to use blob data. This is changing. So again, if you're interested, please look at the dashboard. And another question that was interesting to analyze was how many missed blocks occur after some number of blobs, right? And this is important because if it takes too much time to propagate a block with six blobs, then what are the chances that the next one is going to be a miss? Because the block proposer was busy, downloading blobs or whatever. And so this is something that we looked at. This was actually a question that was raised during the interop in Kenya and that we wanted to analyze. And so Chato allows you to do this kind of analysis. And so this is, again, one of the pie charts that is shown in our dashboard in real time. And you can see that most of the blocks that were missed in the last month occur just after a block with 0 blobs, okay? And again, you have the distribution over here, but there is not such a strong correlation that you will believe that, okay, every time you see a block with 6 blobs, then the chances of missing the next one are very, very high. That's not what you see in this data. And again, there is a post by Tony on that, so also advise you to look at that. Maybe he will mention it later. Yeah, so I think that's more or less what I have today, and then move on to Tony. Thank you.
I think I don't need that. Okay. Can you switch to my computer? Perfect. Yeah, hi everyone. So my part will basically be about how I use Xatu for my daily analysis. And I want to focus especially on PyXatu, which is basically a library in Python. If you're familiar with web3.py, for example, this is basically what I try to achieve here, allowing users to have a very high level, very easy access to the Xatu database, and then, yeah, coming up with some functions, abstracting the complexity of Xatu, although Xatu is not very complex, but of course you can always make it simpler by wrapping in within a Python library. And yeah, so let me show you the GitHub. So you can find my GitHub. There is a PyXatu library, and you can install it very easily by simply doing pip install PyXatu. And then you have to run xatu.setup, which will copy a configuration file into your home directory. There you have to put in your credentials, and then you're ready to go. So if you need credentials for Xatu, I would just say reach out to the Eve PandaOps team. They are very happy to provide you those. And yeah, so as soon as you have the credentials in your home directory, you can already start by doing something like this. We basically, okay, now I have to kind of, pardon? Dimming the lights, is that possible? Can we dim the light if that's possible? Okay, let me see how do you want to hold it? Okay. Okay, let's see. Oh, it's taped. It's taped to the table, okay. Then, very nice. Maybe you want to use that chair. Okay. Okay. So how I would start, it's basically importing the Xatu database, import Xatu. Then I would create the object that basically inherits all the functions, which is PyXatu. Sorry. Right. And then you already see, okay, I'm now connected to this endpoint, and I will then call this endpoint. So in the background, it's actually using SQL queries, but the Python library should allow you to make that as simple as possible. And the first use case that I thought would be maybe appropriate for having a quick demo is, what if we want to know what are the missed slots over time? So first thing I would do is I would have to find the right function. Everything is documented in the GitHub, but basically it's xatu.getMissedSlots. Right. And of course, I don't know which columns are actually behind this data set. So there's a data set called beacon slots or something similar. And in order to know which slot was actually missed, the simplest thing to do is we query all slots, and then we check which slot doesn't have an execution payload, right? Because if there is no execution payload, then this means basically there is no, nothing from the EL in that block, which means either the block was reorged or the block was missed. So what I would do is I would first get the docs from this specific function. So I would just check, okay, I need the get missed slot. I copy it, paste it, and then I can see all the different columns I can get from this data set that is behind the get missed slot function. For example, I'm now interested in actually only one thing. I only want the slot number, right? I don't need anything of any other column. I basically only want to know which slot number was missed. So the query would then look like the following. I would have xatu.getMissedSlots. First, I would specify the slot range that I want to query, which is done like this. Let's say 9 million to 10 million. And the second thing is the columns I want. And this looks like this. And now let's see if this works. Wonderful. So what we get here is basically now a Python set with all the slots that have been missed within slot 9 million and 10 million. And then I can continue by putting it into a pandas data frame. Let's do that very quickly. Oh, I haven't imported pandas yet. Okay. Let's see. df pandas, that would be like missed slots. Oh, I called it df. And then I think I need to specify the column here. Let's see if that works already. Looks good. Okay, that's nice. Now I have everything in a pandas data frame. And the next thing I will do is I want to map the slot number to the actual date, right? This is, yeah, please. This is all mainnet, yeah. So, yeah, I could mention that. When you query for this, sorry, it's actually here. You can also always specify additional parameters. I've skipped it now for simplicity, but basically you could say I only want it for a specific testnet. You could say Sepolia, Holeshki, but per default it's always mainnet. Because this is also very important. If you query Xatu, you always have to make sure that you're not mixing different nets up with each other, right? Because suddenly you get very strange things, I can tell you, where you're like, okay, is that actually is mainnet broken? But then you find out, okay, it's actually a testnet. But thanks for the question. Okay, so the next thing I want to do is basically add a date column. And there you can do the following. So I will use Python's lambda function. That's very handy for use cases like that. And then there is a Xatu helper function. Let's see how it is called. Get slot date time, I guess. Yeah, let's use this one. And I would basically throw in the slot number, because every slot, you know, we have 12 seconds, so knowing the genesis time, we can exactly tell at which time a slot appeared. Let's see if that works. Wonderful. And now we are already quite far. So we have the date, the slot, and the last thing we need to do is then to group by the date. Let me quickly check. Okay. Let me see. Get slot. Okay, there's another helper function that will be simpler, slot today. Okay. Actually, let me use another helper function, because now I got very precise timing with seconds and everything. But in order to visualize this missed slots over time, we don't need the minutes, the hour, and everything. We basically want to have it grouped by day. So there is also slot today, right? And there I would do the same. Right, that's already a little better. And now I want to group that whole thing. Let's see. Group by. I want to group by date. I want to sum up the slots. Basically, I want to count them actually, because otherwise I would just add the slot numbers and then reset index. Just this is basically all some pandas stuff to get a nice data frame in the end. Index, and in the end we can sort it by date. Right, let's see if that works. Perfect. And then to make it 100% realistic, I show you exactly how the workflow works. You can already see ChatGPT is ready. I would basically do something like, give me, I like the library Plotly a lot, Plotly Express chart visualizing my missed slots over the days. Paste in my data that I have, and then I had quite good experience with ChatGPT, so ChatGPT is really good at quickly creating those charts. So first, let's copy the whole thing. So I don't need this sample data that ChatGPT gave me, but I can see it put it into a df variable. So I would do something like df is my group df. And then let's see if that works already. Perfect, right? So this is actually a very simple example how you get to the missed slots. I don't know how much time it now took, like 5 minutes, 10 minutes, but it's a very realistic workflow. So this is how it looks like when I do many of my analysis. Of course, it gets a little more complex, especially if we want to go a little deeper. But for the missed slots, that's actually already it. The next thing we could do is maybe I should ask, is there a validator in this room? Or someone who has a favorite validator? Validator number 1. Okay, let's do Okay, yeah, and they are not yet withdrawn? Okay, let's see. Because one very interesting thing that you will not get anywhere else, but you get at the Xato database, is you can check when your blocks are seen in the network. So you can check, okay, my validator proposed a block, and I want to know when did this block arrive in Europe, when did it arrive in the US, Australia, and so on. And this is very interesting, especially if you want to check who is playing timing games, are your blocks late? For example, if you build your blocks locally, you don't use MevBoost, then this is in particular interest of you, because you might want to know, okay, is my block out there at the network in 1 second into the slot or 3 seconds into the slot, right? Because if your block is very late, then you might want to consider using either MevBoost or, yeah, looking for better peers, and just to make sure that you will not be reorged. Okay, I see validator number 0 is active. Let's do it with validator number 0. So there is a function called xato.getBlockEvent. Block event, that's the one. I will just do the same slot range again, which was, where do I have it? I got it here. Let's do 9 million to 10 million. Okay, now we have to hope that this validator had a slot in this range, otherwise we'll just deviate to another one.
He proposed in August something. He proposed a block in August, yeah.
Okay, then we should find something. First, I do the get docs again, because this is always handy to see what Xato is actually offering here. It's actually .get docs, and then I paste in the function name. Okay, what I need now is the event datetime. So Xato, there are many different nodes all around the world, different clients, everything, and I want to know when are blocks seen by those different clients. And the block and the time seen is here the event datetime, because it means when was this event recorded, and because the events are recorded in real time as soon as they are seen, we should be able to use this event datetime. Then let's see what else we might need. Columns is equal to event datetime. We also need the slot, I guess, and we might need we also need the proposer ID, right? We want to know the proposer, which validator ID did the proposer actually have. But you can see this is, I think, not included in this data set. So we might need another query for the proposer, which tells us which proposer was supposed to propose in which slot. Get proposer. Same range. And again, that's how it works. We go into the docs again, quickly check what is there. There is a slot and there's a proposer validator index. And I would then query those two. Slot plus proposer validator index. And then I should get a pandas data frame that shows me the slot and the proposer index. Now we can go on and merge those two data sets. So here we had the block event, which looked like a slot and the event datetime. Okay, I should have not run it again. Okay, looks good. Perfect, and then we can do something like pd.merge. Proposer. We merge left, and we merge on the slot number. Left on slot. And then right on slot. Looks good. Right, and then we are already getting very close, right? Now we have the slot number, the proposer that proposed a block or was supposed to propose a block in that slot, and the event datetime when the block was seen. Could you come in? The next thing we would need to do is basically group another time because, for example, if you want to know when it was first seen, right, this is very interesting because, for example, if you want to know if someone is playing timing games, you want to know the first time the block was seen in the network. Usually that's in second like 1 in the slot, but if you play timing games, then it's like at second 3 in the slot. And what we can do here is basically group the whole thing. We group by slot and I think it works like this. We group by slot and propose a validator index. And then we take the minimum of the event datetime. Oh, damn. Okay. Okay, let me quickly check. Let me make sure that I didn't forget anything here. Yeah, it looks good. The maximum would be very different because sometimes a node sees a block, let's say, 20 seconds after it was actually proposed, right? For example, if the node is slightly behind or something, so you will find sometimes numbers that are much higher. For example, let's say the, I don't know, Nimbus-Geth combination in Australia had some problems right at that time. Then you might see numbers that are way too high, but usually all those nodes should agree on, yeah, some rough number. And I'm here interested in the first time we saw a block because this tells us with a very high likelihood that this is the time when the block was proposed. The block was actually proposed a little earlier, but usually this should be a quite good approximation. Okay, let me check because I just see I should have done reset index, set index. Let's do in place true. Okay, now maybe there is no in place. Let me try it like this. Ah, okay, that's fine. And now one very interesting thing is you've all seen on Dune dashboards, on my dashboards, we always use those validator labels, right? And it's super hard because you need those different heuristics to create those labels. But you can also use Xato in the future. You can access it under xato.validators and then .mapping. And what this gives you is basically the validator ID, public key, the deposit address, and all the labels that you see on Dune dashboards or on my dashboards about all those validators. So what we could do now is let's first check. Let's just merge it to our data set, what we have so far, which is the same again. Merge, df, we have the labels. We merge on the validator ID. So left, then we do left on. Okay, the left-hand side, it was called propose a validator index. And on the right side, it was called validator ID. Right. Okay, this looks good. Now we have all that information in our data frame. And what we can do now is we can already start looking for what is our target validator doing, validator with the ID 0. Oh. Okay, we want validator ID is equal to 0. Oh, there was no block. Let's try 1. Okay, validator ID 1 had a block in that time. So for example, we can see the time when it was seen, all the other information that we need. And finally, what we can do is there is another helper function for you that is telling you at which time in the slot the block was seen. So seconds in slot. And then we do df.apply. So I apply a function over the whole row. And then lambda x. And then I have to do xatu helper, helpers, and then I will do get time and slot, okay. get the time in a slot. And what this function wants is basically the slot number and the actual time it was seen in the slot. So the slot number, we got it in the slot. And then the event date time. Okay, actually I forgot one important thing here. Just see that I should have converted this datetime into an actual Unix timestamp, but this is very easy. We do it like event datetime is equal to event datetime. And then you can do something like Pandas has a function that makes sure that your field is actually a date format. So datetime, we can say UTC is true because all the times you find in Xatu are UTC. UTC is true, right? And then we can do something like as type, which means we convert from datetime to integer. Integer. And this now gives us milliseconds. We want seconds, which means we do something like 10 to the power of 6. This should be good enough. Let's quickly check if our dataset looks like expected. The event datetime, yeah, we now have the datetime in Unix timestamp. And the final thing we do is exactly this here. We continue with x.event datetime. Right, let me quickly check I didn't forget anything. Looks good. Okay, this is everyone who is familiar with pandas knows why I do certain things. For example, apply one because we now put in the whole row and not only one cell. And let's see if that works. Okay, this is kind of expected. Let's see where the bug is. Oh, it's access one and not apply. Yeah. Right. And what this does is basically we tell him the slot, we tell him the exact time we recorded the event, and using that information you can then tell at which second in the slot was the event actually seen. And now we have all the information we need. For example, what we can do is, let's actually do something like group by. We group by label, and then we do something like seconds in slot. We take let's do the median, and we reset index. Okay, let me quickly check. I think median without the brackets. No. Group by labels, seconds in slot. Okay, there's a typo, huh? Oh, I still called it. I called it event datetime, right? No, I didn't do the seconds in slot yet, right? This one? The S. Oh, thank you, thank you. So this should work, perfect. And then we can do median. Right, and then we get the median time when every validator slot is seen. You can see we've got a lot of, looks like some solo stakers, but then we can also check like, okay, we all know that P2P, Kieln, there are some entities playing timing games, right? So what we could do is we do something like this, label equals, let's do Kieln. So for Kieln, the median time when the block is seen is 2.93. And then we can do the same. Let's see, for example, okay, no block in that time. Wait. Then you can see, okay, that with especially pushing for a blob increase in Pectra, analyzing big blobs, analyzing reorgs, and yeah.
Or maybe it's man in the middle.
Yeah, we could definitely add that if that's something that you.
But
Yeah, so I don't know what I think we use Google on fraud, but yeah, we could,
it's interesting. Oh, okay.
so we can,
It's very
yeah, I mean, you can set
Yeah,
whatever you want, but just
we use a lot of Grafana.
Because Cloudflare's got one.
And then for like individual deep dive
It's like
analysis, we'll do a similar thing to Tiny.
time protocol, like
Pretty much
it involves signatures, but it's much
yeah, a lot
less
of that stuff
accurate.
is in Grafana.
Like NTP can be very accurate, but I don't know if Google's would be considered accurate. Like, I don't know what the state of the art, but
yeah, cool.
yeah, I think there's. I mean, I'm just kind of curious if there's ever a need for more accurate time.
Yeah, we are. Yeah,
Is it,
yeah,
you're studying timing attacks. How should that be?
very-
If anything has
we use
better, I mean, they must have a very good time sync. Is it a phenomenon like if there's bad hackers out there, they must have
All right. Good afternoon, everyone. I'm super excited to be here with you today. And I hope that you're as excited as I am. So my name is Clément, or Clément, with the French accent. And today we are going to talk, and actually we are also going to write some huff. So first I would like to ask you who knows what huff is? Okay, so that's pretty nice. And whoever tried writing some huff already? Okay, so we have a lot of beginners. That's perfect. One last question: are you knowledgeable? Do you know how blockchain works? Are you a developer? What would be do we have many beginners in blockchain development here? Oh, okay, intermediary maybe? Experts? Oh, wow. Okay, I'm impressed. Okay, now I have a lot of pressure. All right. So, yeah, so now you might be wondering, what the hell is Huff? Maybe you know a little bit about it. Maybe you already wrote some Huff contracts. Well, we are going to start with, the basics, with the definition that you can find on the website. So basically, Huff is a low-level programming language designed for developing highly optimized contracts that run on the EVM. So, well, since you guys are experts, you know exactly what this means. But maybe it would be a bit obscure or esoteric for some people. So we can have a look, a deeper look. So when it comes to smart contracts development, you have many different choices. You can use the most common ones like Solidity or Viper. They're the usual languages that people are going to use. But there's a bit more to it. You can use, for example, inline assembly. So just adding some assembly like this, on top of your Solidity code. You can use a Solidity standalone assembly called Yule. You can use Huff. So we're going a bit deeper in the iceberg. And if you're a crazy person, you can write a mnemonic bytecode directly, but I wouldn't recommend it. So obviously, you guys know this is just a very simple Solidity smart contract, very basic. We just have one value. We can write this value, and then we can read this value. Pretty high level, very simple to understand. We have the equivalent in Viper. Same thing, kind of high level. Then here we have something a bit more interesting. So here we're using inline assembly. So we are trying to dabble a little bit with the EVM. Pretty straightforward also, just some different ways to do things. This will be the complete assembly or Yule, so it's the standalone assembly version. So we have a bit more code, but things are still a bit simple. Then, yeah, if you want to have some fun, you have the mnemonic bytecode. So it's just all the instructions with some hexadecimal values. And this is just what the compiler will output. You can also write this by hand, but it might take some time. So now you might be wondering, why Huff? Why should we use Huff? Because we have many options. They seem to be quite reasonable. They seem to be quite flexible. We can do most of these things with them. Uniswap is written in Solidity. We have Curve in Viper. We can do pretty much anything. Well, we have to go back a little bit into history, and basically Huff was created at first by the Aztec team. It was in 2018, and they were working on a smart contract called, bear with me, Wire Strudel. I don't know what this means, but that was the name of the contract, and basically just a elliptic curve, something similar to Zcash. And they wanted to write this in Solidity. They tried it, but the results were not convincing. They tried to use some assembly, but still it wasn't there. So they started to think about making some kind of way to be able to write assembly, but with extra function, extra features. And so this is how they came with the idea of writing Huff, of making Huff. So this is like I think the first Huff code ever written. So you can see it looks like a bit what we have now. Some stuff were removed. I think like like template, we don't have this anymore. But most of the things are still there up to this date. But when Aztec decided to create Huff, they had like very different intentions at what we have now. And like I think I took this quote from their README actually. So they said like Huff was designed with a complete disregard for semantics, safety, or basic consistency. So any similarities to production code are purely incidental, and Huff should on no account be used by anybody. So yeah, this is more or less what they said about Huff. They just wanted to build this tool for them, and the goal was not to really to spread it. It was open source, but it was not meant to be like shared. But what happened? So we know that obviously, if you're here today, like the story and like the road that was like taken is quite big, and actually have evolved a lot since then. One day, like some guy decided to take the code and write like a new compiler in JavaScript, and some people decided to write then a new compiler in TypeScript, and more people came and they decided to write a brand new compiler in Rust, and then more people came and they said maybe it's time to write like a new compiler in Rust again, like from scratch. So we have like many different people, many different contributors. I just took this picture from GitHub. I think many of them are missing, but it's like maybe the main contributors that contributed to the core. Many other people contributed to other things like writing libraries or like making, I don't know, like writing articles or making presentations to have. But this is more or less like all the people that contributed. And this is what I showed you earlier in Solidity or in Viper, and this is like the same code in Huff. So as you can see, it's not that big. It's maybe a bit scary, but we don't have much code actually. It's kind of simple. We are going to go through it in a bit, but first, let's answer this question. So like, really, why the hell should I use Huff? I think that's an honest question, and yeah, let's answer this question. So first, I think what's really nice when you're using Huff is that you have access to like all the opcodes. It's not the case when you're using inline assembly. Even if you're using like standalone assembly, you cannot choose like all the opcodes. You cannot like manipulate the stack, for example. You have like many restrictions. When you are using Huff, you have access to well, pretty much anything that you want. That's the first thing. Also, we've been talking about gas costs. So this chart might be, it's not very like precise. It's maybe a bit outdated. I took it 1 year ago, I think. Patrick Collins shared it on Twitter, so I just like been reusing it. But it gives you like an idea. Like this is like the we are comparing the cost to like create a contract, to deploy a contract. And here we're just like comparing the cost to read and write read and write operations, so using Huff, Viper, Solidity, etc. So it's not exact, but it can give you like a rough idea of how we can optimize the code. Obviously, there are some stuff that are in the Solidity and Viper code that we don't have, but yeah, more freedom. You can do whatever you want. If you want to remove many safety features, you can do it, so you can make your code like more optimized. So some very specific use cases, if you're into MEV, if you want to write bots, if you want to do like very specific smart contracts, you can use Huff because it will be like purely optimized to exactly what you want to do, and you can like reduce the gas costs like in an interesting way. Yeah, you can also do some crazy things, like this guy, for example, wrote Uniswap v2 in Huff, which is quite impressive, actually. I remember some people wanted like to deploy DEX that was purely written in Huff. I don't know if this ever happened, but that was like a crazy idea. We have this also, Hafidity, which is like a way to run half code inside of Solidity by injecting the code. Yeah, it's a bit esoteric, exotic, I don't know, you will call it the way you want, but this is like at the boundary of of what we can do, and maybe it's not a good idea to do this either. But I think like the best use case for Huff basically is just to teach you how the EVM works, so you can become the EVM Chad. Yeah, because what we have been seeing is that since Huff has been created or revived, we can say it this way, many people like me got interested into Huff, and we can learn a lot about the EVM, and then we can get more familiar with it and just become a better developer. So when you will be writing Solidity code, you know exactly like what the code is doing. You can maybe write some optimizations in inline assembly, or if you're debugging something. So it will give you like a better understanding of like how the EVM works, how under the hood everything is happening. And yeah, like today, I mean, it's been a while already, but I mean, like nowadays, there are many tools. Like for example, if you want to write some Huff, you can use like Foundry to test your contract. So it's extremely simple. There's a template for that. And then there are also like libraries like HuffMate. So if you want to write something, then I don't know, like an ERC20, there are already like a template that was made. But I think like the best use case for this library is to just go through all the contracts and try to understand how they work. I think it's like maybe has like all the same contract as Soulmate. Maybe, I'm not sure, but many stuff like Ownable, like many create tree libraries, stuff like that. So it's very impressive also. So yeah, I think now it's time. I made like a small introduction. So I think now it's time to maybe start going deeper into Huff. So I think we're going to do this in two parts actually. First, I'm just going to go through like all the features that we have in Rust, so you guys can get like a more like a better understanding of what we can do and how we can do it. And then we'll get to write some actual code. So yeah, as I said, basically like Huff is like some kind of assembly language with many convenient features. And yeah, first I'm just going to go through like how the EVM works. I'm sure like all of you know, but maybe there's like 1-2 people that are not very familiar with it. So I just want to be sure that we're all on the same page. So this is a stack. This is where most of the manipulations or handle, like if you want to store values, if you want to compute stuff, like everything will be happening into the stack. So the way it works is very simple. You have here like a pile. You're just like stacking values from like the top, the bottom to the top. So you're just like adding new values on top. If you want to remove a value, you will pop the last value that you just added. And what is going to happen is that, let's say we have like A, B, C, and D, and then you want to multiply something, so you're going to use the multiply opcode. Then what is going to happen is that the EVM is just going to take like the 2 latest values, and it will multiply them, and it's going to put them back into the stack. Yeah, this is just like another representation of the stack, so still the same thing. Just be aware we have like plenty of space, like 1024 values. The thing is that we can only get like the 32 first values because we have only like opcodes. For now, we only have opcodes to get value up to the 32nd value. This will change maybe with the EOF, but for now, this is the way things works. And this is why we have like a stack too deep in Solidity also. Then we have the memory, which is like another area to save some values. The memory is very simple. You have like an address and a value. Addresses and values, they are using like 32 bytes. So basically you can just store whatever you want, wherever you want. You just have to follow this pattern. The storage is following the same pattern, and we also have the transient storage, which is also the more or less the same thing. And this is the call data. So call data, when we are referring to it, is just like a value that someone is passing to your contract when they're calling them. So this is a swap on Uniswap v2. Obviously, if you don't know, like, you might not know what are these numbers, but basically in your contract you're supposed to. So don't worry too much about that. But yeah, basically we can see like the first bytes, just the signature of the function. And then all the other values, like after all the zeros, these are just like values like amounts, for example, that are passed around, or maybe addresses. Yeah, just like a very cool website if you want to be or get more familiar with like how the EVM works. You can go on evm.codes. There are many different sections. The first one is like opcodes, which is this is what I showed you earlier, just like a list of all the opcodes. It's just explaining exactly how they work. It's like a very convenient. And then you have the playground, so you can write some Solidity code, Yule code, I think also like mnemonic bytecode, and then you can just hit the run button, and you can see like what's happening step by step into the memory, the stack, the storage, the transient storage, the return values. So it's extremely convenient, and it's a great resource just to use, like to learn how the EVM works. There's like a half fork for this, but might not be updated, so I'm not going to show it here. And yeah, I guess it's time to just go through like all the things we have in Huff. So first, like in Huff, you can like have we have the interface definition, which is something very similar to what we have in Solidity or Viper or whatever. You can just like define functions, you can define events, you can define errors also. It's not there, but you can also do it. And then you just have to pass like some parameters. So this will be useful in two cases, either to define like a function so people can call your smart contract, or if you want to call like another contract, let's say like an ERC20, then you can define the transfer function, and then you will use this definition later on to call the contract. We do have some built-in functions in Huff. So we have the function signature, the event hash, and the error function. These three functions works more or less the same way, and it's related to the interface definition. Once you define, let's say, for example, approve, and you want to call approve, then you will be able to use like function sig, and you put just approve inside of the parentheses, and it will give you the signature of the function, so you can call it. The same thing for the event, if you want to emit an event, or if you want to revert, then you can use that for the error and get the selector. We have also write pad, which is just like shifting a value from the left to the right. And then we have like table start and table size. Basically, it's like a way to write switch statements in Huff. We'll get to that in a bit, though. And yeah, this is what I showed you. Like at the top, we're just defining like two errors, panic error and error. Like that's very original. But yeah, then later on, we want to revert. And then what we are going to do, we can just do like underscore error, and then we just put the name of the error you want to use, and then this will add the selector inside of our code, and then we can just like in this case we are reverting with some parameters, so we can just like store these parameters inside of the memory, and then we just have to call the revert function. So another thing that we can define, actually constants. So I think it's pretty straightforward. You have a number, you can just define like a number, so it's like 0x420. This is an hexadecimal value, but you can also define numbers using like decimal values. Most of the people do it this way. And then whenever you want to use the your constant, then you just have to put the name inside of some brackets, and then we'll just like input the right value. Then we have jump labels. So jump labels are defined within a macro or a function. We'll see what they are a bit later. But basically, it's very simple. You have just like a piece of code, like for example, success here. Success is just defined by this instruction. So like we store something and then we just return. And so what is going to happen, if you look at the top, I think there's like a pointer. Yeah, if you look here, basically we are doing something here, and then we say, okay, we want to jump to the success. So we just have to call the label success, and we jump to it, and this piece of code will be executed. So it's quite straightforward also. You can also do it with jump E, so you can add like a condition to this jump. And then we have functions. So functions can have like arguments that you can pass here. And yeah, there is one weird thing here, so takes and returns. So this is something that can help you know what the function is expecting from the stack and what the function will left into the stack. So basically what is going to happen is that this function is expecting like 3 values in the stack, and after its execution, it will leave like 1 value into the stack. So as far as I know, this is not enforced by the compiler, but it's more like a way for you to just like know more or less what you should have, how you can manage the stack. And yeah, so basically functions. So we have functions and macros, and like the big difference is that functions, they are copied only once. The compiler is going to take the code of your function, and it's just going to put it at the end of all the bytecode. And whenever you're going to call a function, then in the execution of your code, it's going to jump to where the function is. And when the function has been executed, it's going to jump back and keep on with the execution of your code, which is different from macros. In the case of macros, what is going to happen, every time you're going to invoke this macro, then the compiler is going to copy the old code and directly put it in your bytecode, what was compiled. So this means that if you're using like macros, then the size of your smart contract might be a bit larger, but it might be cheaper guys-wise because you will be like avoiding like jumping around back and forth. And also, by the way, yeah, so we don't have it here, but basically macros, they accept like parameters, and you have also the takes and returns indications. So we have like 2 important macros that you need to know. We have the constructor. It works the same way as Solidity actually. So basically, if you want to execute some code when you're deploying your contract, then you just have to put it into the constructor. And we have the main macro. The main macro is well, quite simple. This is like the entry point of your smart contract. So whenever someone is going to call your smart contract, the main macro will be executed. So this is where you want to do like the function dispatching or things like that. But we are going to see that in a minute. We have jump tables, so it's pretty small and a bit long. So yeah, it's just a way to do like switch statements in Huff. So maybe we can see that a bit later. So yeah, let's code. So I think it's time now to write some actual code. So yeah, we need, I hope like you guys all have a laptop, otherwise it's going to be a bit boring for you, I'm sorry. So we are going to write some code. We are going to use the template that is using Foundry. So if you don't have Foundry, you can install it using this command. I'll just give you like a few minutes to start installing stuff. So if you already have Foundry, you can install directly. This is like the version manager, I would say. So you can run this. Maybe I should have put these two into the same slide. I'm sorry. Just tell me if you guys all have the first step done, then we can move forward. If you have any questions about Huff or about how to install things, you can just ask me now, I think. Yeah. Oh, shit. Which version do you have? Package? Okay, is this like the... Yeah, HuffUp should be like the... Okay, check your Wi-Fi. Because I know like the Wi-Fi is a bit long now. It's good. Oh, shit. Try again, maybe? Warning. That's pretty annoying. Yeah, I'm sorry. I'm not sure how to help you here. Yeah. Yeah. Let's see. What is the repo you opened? Oh. Yeah, it's a bit weird. We're going to use Foundry, so it's just going to like do everything. But I think like yeah, it should be working. Try just like have C dash capital V, and then just to see if. Yeah, I mean it's saying compiling. So yeah, you have the right version. Yeah. I think if you want to output something, there is like a command. If you try help, it will tell you. Yeah. There is something like an output, yeah, bytecode, stuff like that. Yeah, it's a bit weird. No worries. All right, so if you guys have Foundry, we can move forward. Then you just need to install Huff, and once you've done this, you can install. So this is installing the package manager, not the package, sorry, the version manager. Then you can install the latest version, and this should be working. So you should get like Huff. 0.3.2, something like that, and Forge, whatever, like should be working, should be giving you like some outputs. Yep. This one? Let me see if I can give you like all the commands. That would be easier. It's not loading. All good? Yeah. You have Linux? Okay. Oh, it's still installing. Oh shit. Yeah, I hope it's not going to take too much time. Yeah, worst case scenario, like I still have some slides so I can show you guys, but it would be better if we can just like code along. Yeah, all good? Nice. Yeah, installing, downloading. Okay. All good over here? Nice. It's half C. Nice. Perfect. All good. All right, installing. That's nice. All right, I'm just going to give you a few more minutes because I see many people still downloading. It takes a few minutes, I think, to install everything. Did you? Oh, you built it? Okay. Oh, perfect. Nice. All good. All good here? Yeah? Okay. Do you guys need help or are you good? Good? Yeah, thank you. Okay. Yeah, you have like both versions? Everything is working? Ah, perfect. All right, yeah, let's move forward. Where's the clicker? Yeah, we're just going to be writing like two very simple contracts today. I don't know how much time it will take. Like we have 2 hours, but yeah, since you guys are experts, I'm joking, but like I feel like it will be pretty straightforward. So maybe it will not take like the whole time. Yeah, if you do half up, you do half C dash capital V forward dash capital V. You have if you have everything working here, then what you can do, you can clone this repo, just like a very basic template I've made using the actual Foundry template. So you should be able to clone this. I just hope it's public. So just let me know if it works. And when you have this, there will be like one extension. If you're in VS Code, there will be one extension that is suggested. It's called like a half language by half language. And it will just give you like a syntax, like colors, stuff like that. There is also debugger, but we're not going to use that today. So yeah, just let me know if like, okay, perfect, good. I'm relieved. Nice. It should be, so do you have VS Code? If you open the repo in VS Code, it should like pop up the suggested extension. Otherwise, it's called like half language, I think. You got it? Perfect. Yeah, it would be better to be using having some colors, otherwise it's going to be a bit hard just to see what we're doing. Yeah, I'll just give you a few minutes because I think the slide just after this, yeah, like after this we're just going to be cooking. So I just want to be sure that everyone can follow. Oh, you can just decline this. Yes. Nice. But I'm right. Yeah, perfect. Okay, good. Yeah, looks like we are all set. So what we are going to do, we are going to be writing our first half contract. So I think there might be a source folder, if maybe it's not there anymore, I don't know, but you can just make like a src folder, and then you can write the first like create the first file. You can name it the way you want, compute.half or whatever you want, and then we are going to be writing some code. So this is the first contract we are going to be writing today. It's extremely complicated, you will see. This contract is just going to take two values and multiply, not multiply actually, add these values together and then just going to return them. So as you can see, it's extremely hard to understand. Yeah, so let's just like follow along. If you guys have your setup already, you can code at the same time. So the first thing we want to do is that we are just going to define a function. So here, as you can see, this is what we're doing here. Let's call it, I don't like compute. You can call it add or whatever. It doesn't really matter. So this function is going to accept two parameters. So we need like one uint256 and why not another uint256. And then it's going to return, well, something very original, one uint256. So this is just like the function that we define, and this definition will be used by us inside of our Hub contract, but it will also be used by the people that want to interact with our contracts. So then we have this, which is a macro here that we are calling compute. So we can define this macro here. Just a way to organize our code. It will be also, another way would be just to shove everything into the main macro, but that's, now we are like educated people, so we are not going to do that. I'm going to go through what's in there in a second, but first I want to talk about the main macro, which is just here. So as I said earlier, the main macro is the first thing that is going to be called when someone is calling your contract. This is like the entry. So in our case, it's pretty simple. So let's go through it. So okay, you guys can. So maybe you're writing at the same time. So I will slow down. I'm sorry. So yeah, first I think the easiest thing is just to write the first function definition on top, and then you can go directly to this. Don't write this so now, we'll do it just after. Yes. Yeah. Here? Oh. Yes, yes. So why are we returning nothing here? We are not like leaving anything in the stack. It's because we are returning here, and this return is actually the end of the call. So when we are returning something in Hub, we are actually like returning values from the call. So it's like the end of the call. I know it's a bit the names may be a bit confusing, right? Yeah, because we have returns which is not actually returning but just leaving stuff in the stack. So that's true that it can be a bit confusing. So yeah, I'll just are you guys ready or not to go through the main macro? All right. Okay, let's go. So now we are going to do what we are calling like function dispatching. We have like a very basic implementation, but it works the exact same way. For example, in Solidity or Viper, there are many different ways to do this, but this is like the most common way. So basically, what is going to happen is that someone is going to call our smart contract. They will send us some call data, and we just want to know, okay, what do they want to do? Like, what is going to happen? So what we are going to do is very simple. We say we want to load the call data, so all the values that were given to us, but we want to load it starting from like the first byte. We want to load it from the start. And then maybe you know this or maybe you don't know, but basically like function signatures, they only have like 4 bytes. So how does it work when someone is calling a contract in Solidity or like in the EVM? Like the standard is that when you're calling a smart contract, the first bytes, the 4 first bytes are the function selector. So what you are going to do is that when you receive the call data, you are like, okay, I want to know which function we should call inside of our contract. So I'm going to check in the call data what the guy wanted me to call. So we are going to load the whole call data here, and this like magic number, the value is like 2024 bits. So it's like 28 bytes. And so what is going to happen here? We put in the stack like the whole call data. So we have everything, and then we say we want to move to the right, like all the call data. So we are going to move everything to the right, but we are moving to 28 bytes. So we are going to leave a value which is only, well, you can do like 32 bytes minus 28, and you have 4 bytes. So this is like the function selector. And so, yeah, we have a function selector. So we know which function the sender wants to call. But now we need to check, okay, so do we have this function? Maybe we don't have it, maybe it's a mistake. So what is going to happen here? We are going to do exactly like the function dispatching. So we are going to load here our function signature. So this is what we have. Compute, it's here. This is what we define, and this is what we are expecting. And then we're going to do like equals. So equal here is going to check if what we loaded here, what we sliced from the call data, the function signature, function selector we have, is equal to this one, the function signature that we are expecting. And then we say, okay, so if it's equal, then we'll have a 0 here. We'll have a 1. If it's not equal, we have a 0. And then we are just going to call the jump if opcode, and the jump if opcode is very simple. If this is 0, then we are just going to continue. If this is 1, we are going to jump to here, compute, the jump label I showed you. I explained to you this earlier. So maybe this is a bit confusing. Just let me know if we need to slow down. Okay, you have a question. Go ahead.
On the function signature, what is it doing exactly there? On the function signature, how is that? Could you dive deeper into that?
Yeah, sure. So basically, this is the same thing as Solidity when you have like encoding something, or if you define a function in Solidity, you can get like the signature, you can get like the 4 bytes. And this is the same thing here. We define this function here. Like this is like our function.
Oh,
and
I see. So it's actually computing the signature, function signature from the compute.
Exactly. It's computing the hash. So the hash of this, and then it's just going to slice and only get the 4 first bytes.
Okay. Could you go back a little bit on the call data piece? So is it just leaving on the stack the 4 bytes of the function signature?
So basically here we are going to, it's a bit weird because like, you have to add the value on the stack and then you call the instruction. So it's a bit hard to explain because I need to explain like back and forth what the values are. But basically you're like, I want to, from the start, I want to load the call data. So you will be loading the call data from the first byte, from the byte 0. But you are going like to load 32 bytes. What is going to happen is that this function is going to take like a slice of 32 bytes and put it into the stack. So you will have 4 bytes for the function signature, but then you will have 28 bytes, which will be like nonsense.
The parameters.
Yeah, it will be, in our case, it won't be nonsense, but it will be this, the first parameter, but it won't even be like the whole parameter because this is like 32 bytes. So yeah, maybe yeah, I should have put like a graph or something. It's hard to explain this just like this, but
Yeah, it would be helpful if you had like the stack on the right
yeah,
hand side.
good idea. I'll see if
visualize
I
it.
can do something. Yeah, I'll see if I can do something actually after. But yeah, basically the idea is that you're loading here 32 bytes of call data starting at the position 0. But in this case, we only want the first 4 bytes. So we say, okay, let's just move to the right this element in the stack, and we want to move it to 28 bytes. So we move it like this. And so we are left with 4 bytes, which is the function signature.
So on the stack, all that's left from the call data is the first 4 bytes, which is the function signature.
Exactly.
Got it.
And after we just check, okay, is this like a valid function signature? Because someone can just be like spamming our contract. So we need to do like a proper check. Which function do they want to call? So we are going, sorry, we are going to use, we are going to load our own function signature, what we define here, into the stack. So basically the stack we will be their function signature, our function signature on top, and then we'll just do like equal. And both values will be removed, and equal will just leave a 0 if they're not equal, if they are not like the same, and it will put a 1 if like both signatures are the same. I just want to, yeah, there is like here, duplicate 1. This is not needed here, so I'm not going to talk about it. We'll see that after, but this is not needed here, so don't worry about it. And yeah, so we are checking here, and yeah, like the final thing to do is just to jump accordingly. If the function signature is valid, if we have something that we are expecting, then we jump here to compute. And in our case, we decided to make things the proper way, so we define like a macro for compute. The other solution would be just to shove all the code here, but it's just cleaner to do it here. And yeah, if they don't have like a valid function signature, we're just going to revert. We don't care. They are not like asking for the right function, so we are not like reverting with any extra data. We're just returning 0 value, just reverting the transaction. But we could have been like reverting and say like anything you want, like wrong function signature or whatever. All right, do you have any questions? Yes, I'll give you the mic.
I see by the looks of the function and the main functions, you have a revert and return. It's all recursive inside of the EVM, or it's just for showing they have a revert or return function?
This or opcodes?
Yeah, I refer this, the EVM is recursive when the codes.
Oh, do you mean like, is this going like to fail the whole transaction, or?
Continue the transaction, the execution, until you put the return on the revert, or revert.
Yeah, if you revert here, I mean, it's the same thing in Solidity. You can revert here, but then the call can continue. It's the same.
Continue infinitely until the gas.
Oh, no, sorry. Okay, I understand it not the right way. This is the end of the transaction, but it will continue if there are like more things after. Other opcodes to execute, but if you reach like the end, like in this case we are reverting, but it depends on like well how you're writing your contract and who is calling your contract, because like if you, I don't know, like I mean it depends. I don't know exactly how to answer this. But yeah, like basically it will consume gas, but if you reach the end of the call, then it will just stop consuming gas. You know?
Okay.
Because it's only consuming gas when it's like executing operations, but if there is nothing left to execute, then the transaction will just stop.
Okay, so if I remove the return or the revert, it just stops completely.
If you do that, if you remove the return here, I'm not sure what it will do actually. That's a good question. I think we'll stop because this is here actually in like the code. This will be compiled at the end of our contract, and then if you do this, then after the contract has ended, so I think it will just stop. But otherwise, you can, if you forgot something, you can make a loop. If you put like here something, then it will jump here and go here and jump here. Like it will be a loop. It will consume all the gas and just revert with out of gas, actually.
Okay, perfect. Thank you.
Question about the 0x00 call data load.
Yes.
There. So that sounds a bit heavy. Is that the most efficient way of getting extracting the selector?
Mm-hmm.
Okay, cool.
Yeah, because you can, when you're using like call data load, you can only load like 32 bytes. You're loading like a whole piece of information into the stack. Then you have to move forward to get the actual function selector. There is another way actually, and I think you can load like a single byte from the call data, but that is not standard. So you can do it, but it's not like the standard way. So you could be like loading, I don't know, like the first, you say, okay, this is like 1, and if this is 1, we compute, or we go to something that will add. If this is 2, then we can go to something that will do minus, subtract, things like that. But the standard way is like 4 bytes. Yes, so we can continue. So basically, once you once you are going to compare here, and then you have, like, as I said, like 2 different cases, 2 different scenarios. Either you can revert, so we are just reverting like the hard way, or we might be going to our macro here, and the macro is kind of simple. So we know that we have like 2 uwins 256 that we need to have into the stack because we want to add them together and return the sum of these 2 values. So we are going to do the exact same thing as we did here. Call the same function. And so in this case, we know that the 4 first bytes are the function signature. So we are going to ignore them. And we say, okay, put into the stack, so call data load, but put into the stack the call data starting at the bytes 4. So ignore the first 4 bytes and then put the call data. So this will take 32 bytes of call data and put it into the stack. Then we just have to compute, and we say, okay, we already loaded 4 bytes for the function signature. We already loaded 32 bytes for the first parameter, the first uint 256. Then it looks like it could be 36 bytes that we already loaded. So here's the value, 36. So we are going to say, okay, you have to load into the stack the next value, which is located after 36 bytes. So am I clear? I know this is a bit a bit heavy. If you have any question, feel free to ask them. I don't want to lose anyone, or maybe I already lost some of you. I don't know.
So back to the first couple of lines inside main.
Here.
So I get that we're putting the function signature on the stack.
Yep.
And then, so at the end of the second line, is that if it's equal, then compute jump, or does it say if it's equal compute? I guess I'm getting confused a little bit on the naming conventions, and like you've got, you know, you're defining function compute, and then you also have a label compute, and so
don't worry, I'll explain. So basically, okay, I understand what you mean. Okay, so the naming was maybe a bit wrong, but basically here compute we have our function, and this is only related to this. This and this are related. That's it. And then this compute is the jump label that we are defining here. So these 2 are related, but that's it. There are no other relationship. And so.
Okay, sorry, one
Yeah.
final thing on that. So
Go ahead.
where it's doing the equals, does it know automatically to just pick the first one off the stack and then compare it to
Yeah.
function and signature compute?
So because here we loaded like the function signature from the call data, so we have like at the top of the stack we have one function signature, the one that the sender gave us, and then here we are loading, we are putting into equal, and we'll say, okay, I need two elements from the stack, two values from the stack, and we'll just take like the two first values, which are the values we need. And then, so we have into the stack like either 1 or 0, and we say, okay, we might want to go to the compute jump label, which is here, and then we say, okay, go for it, but only if we have a 1. If you have a 0, then keep on reading the next code. So it will just keep on reading the next code, which is just like reverting, and revert just say, okay, I want to revert, do you want to return some values from the memory? But we say, yeah, return 0, like 0 value from the memory. That's it. The return here is very, very simple. More questions? Yes. Yeah, basically, yeah. And so this is like the most, I think, convenient thing when you are like writing stuff like this, because if you want to try to write like mnemonic bytecode, basically you can write all of this without huff, but instead of having like compute here and here, instead of having something that you can read, you will have to put like a value, and this value will be like a location inside of your code. So you will say, for example, sorry, I want to go to like the in my code to the location, I don't like 148. But if you add more code here, then you have to change this value, you know. So this is just for us to be able to do this like in a convenient way. Yeah, so we are jumping to compute, and as I told you, just like a macro, so it's very, very simple in this case. We are loading our two values here. We know that we have to avoid the first 4 bytes, so this is like the next 32 bytes. This is the next 32 bytes after the first 36 bytes. And what is going to happen is that we have value A and value B inside of the stack. So we just have to call add, and add is exactly what I showed you earlier. So it just like with multiply, just taking like two values from the stack, it will add them together, and boom, they are put back into the stack. And what is going to happen here is that it's pretty simple. You'll see we have one value into the stack. And well, now we want to return it because we did all of this, but now we need to return our value. So return here is very simple. You can only return stuff from the memory. So we have to put our result, the sum that we just computed, into the memory. It's very simple. We are going to use the mstore opcode, and mstore takes one value here and one location inside of the memory, and then we just call mstore. So what we've done here is that we are putting here at the location 0 the value of add. So the value of add can be anything up to 32 bytes, obviously, but it can be anything. And yeah, we have like value in the memory. Yes. Wait for the mic. Sorry.
Isn't there a cost for putting that value in memory? I mean, it's not like...
Yeah, obviously.
Yeah, but why not return it from the stack?
Because it's not possible.
It's not possible.
Yeah, the way you can see, like, I'll show you. Okay, let me just go back a little bit. Oh, okay, we are here. So basically, you can see like we don't have the return function here, obviously. Okay, but if you go on this website, it's evm.code. You will see like all the opcodes are explained here, and you will see like stack input. So basically, this is like when I was talking about the stack, this is like what is expected, and this is what will be left into the stack. So in our case, we are taking like A and B, and we are adding them. So we go from two elements to one element into the stack. And you can see like there is a description here. And if you go down, let me share my screen actually, because this is like an interesting question. Can you, yay. All right, let me see, EVM. All right, so if you go down here, I'm not going to take like too much time on this, but basically, yeah, let's do a research mstore here. You can see like, this is explaining how mstore works, and if you go to return, you will see like the explanation. It will just tell you, okay, stack input. So the definition is like the offset and the size. So basically, this means that we need to tell where we want to load the value from. So obviously inside of the memory and the size. That's it. So if you can you go back to the presentation? Thank you. Perfect. Yeah, so it's just how it works. We don't have a choice in this case. But I just wanted to show you the website, because it's going to explain to you exactly like all the opcodes work actually. It's pretty interesting. And even if you are not doing going to do like some crazy things with Huff, if you just use like evm.code and this and Huff, then you can just learn and have some fun understanding how things work. It's still quite interesting. Oops, I went way too far. Yeah, no, wait. This is the second one. This is the test.
That's the one.
Yeah, that's the right one. So yeah, and then we have yeah, as I just said, like return. So return is expecting two values. So we have the first value, which is the size of what we want to return. So in our case, it's 32 bytes. So it's like 0x20 in hexadecimal. You will see like many have code are written, like all the values are in hexadecimal. I guess because it's cooler, I don't know, but it's like more by convention. So you know that you want to return a uint 256, so you have to return 32 bytes. And this is the location in memory. You can see we just stored it here at the 0, like like madmans. And so we can just like call return, and that's it. We have our whole contract. So if you guys have the code ready, you can try writing a test, actually. So this is how tests are working with Foundry and Huff. So we have something called like a Huff deployer, and this is pretty convenient because it's going to take your contract, compile it for you, and then you can just deploy it. So if you're familiar with Foundry, you will see it's the exact same experience as writing regular tests. Very easy, very simple, very convenient. The only small difference, I think there might be a better way to do this, but we'll do it like this today. We just need to redefine our interface here. So we say this is our contract compute, and then we just like copy paste what we defined here. We just need to put it again here in an interface. I think there's a better way to do it, but I'm not going to show it today because, yeah, we might be running out of time. So yeah, this is quite straightforward. You make like a new test file, then you just have to put like compute test, is test, whatever. Just like storage value for your contract. And then what is going to happen is that you just have to cast it. So we define the interface here. So you just cast it, or you can keep the address as you want. And then you're just going to use the Huff deployer, and you do like that. Sorry, you do like that deploy, and you put the name of your contract. I think the name of the contract is actually the name of the file. Yeah. So if you do this, the contract will be deployed, and then you can write your first test. So in this case, we're just like expecting random values that would be fuzzed. And yeah, we say, okay, so the contract should return C, and we can just check that C is the sum of A and B. I'll give you a few seconds. Do you have any questions or anything like that you are struggling with? Like I know this is a lot of things all at once. It can be a bit tedious to set up everything. So if something is not working, we still have like less than 1 hour, but we can take some time to fix some issues.
Can you just explain the math a little bit? Obviously, you've got unchecked there, so all of these UINT 256s can wrap.
Yeah.
And yeah, just explain the bounds on the. Is it just?
Yes. So I'm just doing here unchecked because if we go here in our, I'll go back to the next slide. I'm sorry for those who are copying the code. But if you go here like add, we have no overflow check. So if we are just doing like assert like the sum here and we don't have unchecked, then Solidity will do like a overflow check, and then the code will revert, or we won't have the same result as our Huff code. But yeah, that's an interesting question, because here in Solidity now we have the overflow check, but we don't have it in Huff. So maybe like something that you guys can do is a way to prevent the Huff contract from the sum from overflowing. So that could be an interesting exercise. I think there's already a like a small library in HuffMate that can allow you to do this, but it could be quite simple to code actually.
Hey, sorry, one more question.
Where
you
are
mentioned
you?
that
Oh,
over
yeah.
here. Bit off topic, but you mentioned that advantage of using Huff is you have complete access to all the opcodes.
Yes.
What is one use case that you've found where you can particularly exploit that to achieve something that you haven't been able to do in another language?
So personally, I haven't been coding for production things. I was more, as I said, like in the beginning, I really wanted to learn how the EVM was working, and actually just like writing some Huff was like the best way, because writing resources is a bit tedious. But otherwise, like I've seen many people doing like MEV boats or things like that. They're using Huff, and yeah, I mean like you have more. You have access to many things, and what is interesting also is that you're not writing Solidity code, you're not writing like or even Viper, so you can do like as we saw earlier, like the function dispatching. If you are just writing your own bot for your own purpose, you don't care about that. So you can remove like a lot of the safety features from Solidity, because if you know exactly what you want to do, you can achieve it this way. But yeah, like some stuff also in like main differences. Also, you have access to more opcodes. I don't have like an exact example here, but I would say yeah, like there are so many other cases. But for this one specifically, I'm sure we can find it, but I don't have it in mind. Yeah. 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 Could be an example, yeah. All right. So, yep. Okay, let me see. Oh, you put like you went 8. Yeah, just put like 256. Yeah. Yes. Yeah, I think, yeah, if you have like compilation failed, I think there is one step that we haven't been doing yet, and it's just installing the packages. So if you have this, obviously if you have the first contract and then you have this, then you can try, just be sure to have everything installed. So you can just run like forge install, because now you might not have the deployer module or whatever it's called. And then if you run like forge test, it should be working, I hope so. I tried it in my machine. Same thing, like here, you went 8. The result should just use like 256. Yeah, let's see if it works. I hope it will work.
Oh yeah, it's because they have a. I have an idea. I have an idea. I'm gonna put 8. No, I'm gonna put 8.
All right, let me know if it's working. Yeah, the test is passing. Hell yeah, yeah. You have the mic.
Is there a way to write half codes like inline in Solidity?
Yeah,
Like-
actually,
like-
there is one. This is something I showed earlier. Like there is something called Hafidity. I guess it's called this way. But this is very, very experimental, and like this is leading to many. Where is this? It's here. Yeah, so it works, but I don't think this should ever be used in production, because like the way it works is that it's just injecting, it's compiling your code, it's injecting your code. So I think I mean, if you if you really want to use Hive for something in production, I guess like something interesting would be just to have like a deploy maybe a library or a contract. So I don't like some kind of precompiled, just make a contract that is computing something, you deploy it, and then you can call from Solidity, you can call this contract. But yeah, like this is highly experimental. It hasn't been updated in a year. So I think it was more made for fun than something else. So are all the tests passing? No? You forgot the unchecked. Sorry, I just I just saw this. Yeah, if you, because so basically you had the exact issue that I was explaining. So like here, if you don't put the uncheck, then the test will revert, because adding these values will cause an overflow, and we still have like overflow checks in the test. Any issues? Okay. All right. So we covered the first contract. Yeah, I have another one if you guys are interested in. We still have 45 minutes if you want to suffer a little bit more. A failing test? Okay, let's see. Okay, did you put the unchecked?
Yes.
Oh, shit.
I mean,
Yeah. That's okay. Let me. Okay, the code. I think the half code looks great.
I don't know. Actually, it's just naming convention if you do it like this and foundry, right? So
It doesn't matter. Yeah, that's unfortunate. Okay, if the tests are failing, you can still check if you open on you can open this like a URL in your browser, and you can check, or you can change the branch directly. I've made another branch called finish, and you should have the first test. This one, I mean the contract and the test. I hope they will work, but if they don't work, maybe there's a bug in my code. I don't know. So if you can find it, then that would be amazing. But maybe I made a mistake somewhere. Yeah, so it's passing. So what I'm thinking now, maybe, I don't know, maybe some values. Yeah, you found it? That's pretty funny. Do you have, yes? Yeah, when you're returning something.
Yeah, but like, what if what if it's in the stack? Like, suppose there's an add operation happening on these two values, which are in the stack, and instead of doing mstore, like you also mentioned that if there are two values in the stack, and if I perform an operation on the top two values, then those values get replaced by the result.
Yeah.
Speed, right? So the result is in the stack now.
Yeah.
Can't we return from the stack instead of like store, like the question he asked?
You cannot return from the stack. You need to put into memory. This is the way return works. Return can only read from the memory. This one? Yes.
I think I have something wrong with the installation, so I cannot find the file.
Oh.
But I did like force install,
Force install?
build, and then force test.
Where's your... try to rename this to source, SRC. Yeah, here. If you put contracts, I think it won't work. It's just naming conventions. Try this and let me know. Yes. Compute is the name of your file. Yeah. Yeah, yeah. Yeah, actually, I think I know. Maybe it works? Okay, perfect. Okay, let's see. What's the issue now? Counter example. That's funny. Okay, go back to the file. Yeah. Let me see.
This capitalized. I think this is capitalized here.
Yeah. No, the problem is in the code now. Let me see. Call data. You're loading the right call. Oh, you forgot add. After call data. No. Before. Yeah. Nice. All right. Any issues? Still failing? Oh gosh. Yeah. What was the issue? No compilation. Try to do like a. Yeah. Try to run. Do like force test -- force. Oh shit! What? Oh shit! It's.
Okay, 1 second. Let me just like assert, remove, assert equal. What? Okay, it's not reverting here, I think, right?
That's weird. Why is he running a test if you don't have a test? Oh, it says revert.
Yeah, like I think it's reverting here now.
Oh.
You jump to compute.
Yeah, I'm not sure exactly. Check on the other branch. You can switch the branch. Go to the finish branch if you want. Yeah, if it doesn't work after, I can look into. But I think we are going to move forward because I feel like you guys have the code working. So yeah, we still have like 40 minutes. So maybe we can go through another contract. Yes, so this one is more or less the same thing. No, it's not exactly the same thing, but we are going to cover one extra opcode. So now, in this case, what we want to do is that you will see it's very simple. We just want to be able to get a value from the sender and store this value. And if the sender wants to read this value, then we are just going to return it. So once again, very, very basic contract, but this will allow us to cover a few different things. So in this case, well, we are going to start by the interface definition once again. So we are going to define two values. The first value is just two functions, sorry. And the first function is just set value. So in this case, we want, well, u into 56, which is very original. And then we're just going to make like another function called get value. And in this case, we don't want to set something, but we want to return something. And then we are going to cover something else. So we are going to make a new constant called value location. And so we are going to use this, which is like some kind of built-in function that we haven't seen yet, called free storage pointer. And basically what this function does, it's very simple. It's just going to give you a location where the storage is free. So in this case, if we call it now, it will be 0 because the first location that is free is located at index 0. Very simple. If you call it again, it will be 1 because we have this value already taking the first slot, so the slot 0, and then after we can take the slot 0, 1, 2, etc. Any questions? No? All right. And then we are going to go directly to the main entry point. So this is going to be almost the same code as we did actually. So we are loading the call data from the start. We are shifting to the right 28 bytes. And what is going to happen here is that I told you earlier that we don't care about the duplicate one, the dup one, but in this case we need it because what is going to happen here that here we have the function signature that we received from the sender in the stack. And we want to keep it for later. So we are going to duplicate it. So what is going to happen is that we will have 2 times the function signature we received from the sender. Then we are just going to be doing exactly what we did earlier. So we are going to load, for example, the first set value, the signature of the set value function. So we want to check, okay, maybe the sender, they want to set the value. Okay, let's see. So yeah, we load the set value function signature and we do equal. And yeah, maybe it's equal, maybe it's not, we don't know. So we said, okay, you can jump to set if the value that we just received is equal to set value, and then you know the drill. It will go here and then to the macro set value, and it will go here. But if it's not the case, then what is going to happen is that, well, jumpy is just going to do nothing, and so we will go back here. And in this case also, dump one here, like dump one, sorry, is not needed, but yeah, don't worry about it. But this means that here, when we called equal, we consume the first value that we loaded here, and we consume this value too. So luckily, we duplicated this value into the stack. So this means that we have value A, 2 times the value A, then the value B, and then they are consumed. So we are left with the value A. So then we can load the function signature of get value, and then we have the value A and the signature of get value, and then we can do the same thing again, equal, and if it's equal, we can jump to the get macro, and so we go here, and then whoop, we execute it here. It is clear or not? No? I'm sorry. Do you maybe you have a question and you can answer, like you have a specific point that you don't understand, and maybe I can explain it like in a different way. Can we have a mic over here, please?
Thank you, Clément. So dup1, is that duplicating the...
Yes.
Okay, it is duplicating the stack.
Exactly. The dup1 is duplicating the first item of the stack.
On the stack. So
yeah,
it's duplicating the call, the function signature.
of the sender, yeah. So
Of the
it's
sender.
duplicating the function signature that we received. And so basically, the dup1 here is just a way for us to avoid doing this again.
Okay.
Because we could be doing this, and then we do this, we don't duplicate. But if it's not like, if the sender is not willing to execute set value, then, well, we have to check if they want to execute get value. So we need the function signature again. So we could be doing this again, but it will be costly.
Got
It
it.
will cost
Okay.
a
So
lot
then,
of gas.
don't you have the function signature on the stack 3 times? Because you called duplicate 1 twice.
Yeah, this one is an error.
Oh, okay.
Yeah,
Okay.
I'm sorry about
all right,
that.
all right,
This
all right.
one is an error because I just like copy pasted that
Got
line,
it.
and
Okay.
then I changed this.
I mean, there's no harm because you're not doing anything after that.
Exactly,
But you
exactly.
do have the function signatures.
This could be
on-
leading to some issues. In our case, we are just reverting right after, so it doesn't matter. But I can show you after, like, for example, in the case of ERC20 or something like that. But yeah, you can have like many different things, so you will duplicate every time. But on the last time, it's not needed. You're right.
Okay, all right, that makes sense. So, a question. So when you do the equals, it's
Yes.
actually taking 2 values that's on the stack. Well,
Yes.
no, well, taking one value that's already on the stack, and the other value is the one that's computed as part of that call.
It's taking, like, when you're doing equal is going to take, so this, so we have this value in the stack.
Right, that's on the stack, and then
So you can imagine that here we duplicate, so this means that this value is here. It's like we are cloning it. And
Clément,
equal,
if you don't mind, I'm just going to interrupt you really quick because
Yeah.
the question I have is the function signature that looks like a macro. Is that putting the value of that? It's computing the function signature of get value, right? And is it putting it on the stack, and then the equal function is computing the equal between those 2 values that are on the
Yeah.
stack? Okay, thank you.
Because so this is exactly what you said. Here, equal is going to take the first element of the stack and the second element of the stack. So that was duplicated from this. So we have like here our stuff that was computed and added to the stack, and then the stuff we just computed ourselves.
Perfect. Thank you.
Yeah, and then it's kind of simple here, like to set the value. Well, we just go to the macro here, set value, and well, this is exactly what we've been doing earlier. We know that we need to avoid the first 4 bytes because this is the function signature, so we don't really care about it. So we just do, okay, we want to load 32 bytes starting after the 4 bytes. And then we are going to use a different opcode that we never used called store. So you can see like previously we've been using mstore, which is very explicit memory store. And in this case, we want to store in the storage because the user is setting a value, so we want to keep it for a long time. So we are going to call store, and store works in a very similar way to mstore. It takes like one location and one value. And so what we are doing here in this case, I showed you this earlier when we talked about constants. We are just going to use like within brackets, we are going to call value location, which was defined by free storage pointer, which should be 0. So this means that we want to store in the storage at this location the value that is starting at the call data after the first 4 bytes. So kind of simple, it's just weird that, I think the weirdest thing here is that you're just doing things in reverse. You have to put element in the stack, and then you have to call a function that will take all the elements in the opposite direction. So it's a bit weird to think that way, but you get used to it. And yeah, like you mentioned like many times like the stack, how it works. And so like a convention some people are doing, and actually I think there's a tool for that. Some people here like add comments, and within the brackets they just put what is in the stack. So they will say, okay, here we have a value here. So because we loaded this value, and then they say we have a pointer here. So the stack is like the pointer and the value, and they say, okay, we are calling storage store, so it's going to use 2 values, so then the stack is empty. So it's like also a nice way to be able to track what you're actually doing.
Question?
Yep.
So on the stack, what is the first argument? Is it the one at the topmost, and then the second argument is the one below it?
Yes.
Okay,
so when you're calling
order.
a function, it will take like the one at the top, and it will go like it will remove them one by one. So it will always take what is on top.
Okay, so the topmost one is the first argument in the function signature, and then the second.
Yeah, in this case, I would first use like the function signature. So if you are doing like minus, you will do this minus this. Yeah, so this function, this macro, sorry, is kind of simple. And then I think there might be an issue actually with the code. Yeah, okay, let's see how it works. I wrote this. The test was passing actually, but I think there might be an issue from what you were saying earlier. So let's see. Then the get value macro is kind of similar to what we've been doing, but yeah, we're just going to use like a new opcode called storage load, and it's very simple. You just say I want to load into the stack. I want to load I want to load into the stack the value that is stored at this location. So we're just going to use our value location constant here. We put it into the brackets, and then we just say, yeah, I want to load this value, and the value will be put into the stack. And then same thing as before, we put this value at the position 0 into the memory, and then we call return, and we say, you can return 32 bytes starting at the position 0 from the memory, and it will return the value. So kind of straightforward, yeah.
Just a different kind of question here. If there's a smart contract that's been deployed, but the code was not published, can you decompile it into Huff?
I think there's a decompiler, yeah. I'm not sure if it's really powerful, but I think there's one, yeah.
There's one. Because I was just thinking in terms of reverse engineering the smart contract, right?
You can use it actually. Yeah, that's pretty nice. And more convenient than reading the bytecode directly. Yes, so I think that's it for this contract. It's kind of straightforward. We already saw like the function dispatching and like to store into the storage or to load from the storage. It's very simple. Yeah. Do you have any questions so far? Yeah. You put a stop. I'm not sure. Yeah, I think it's needed. I'm not sure if it's needed or not. Okay, let's see. You can check with the other branch. Go to the finish merge. Code is the same. Okay, I'll let you check and I'll be back after. Any extra questions? Yes.
How does Huff compare to YOL?
Well, I think like, well, the main difference is that, as we were saying like earlier, you have more power in the sense that even in YOL you cannot manipulate the stack. I think there are a few things that you cannot do. In Huff, you can like you can like duplicate elements in the stack. You can like swap them. Yeah, you're free to do whatever you want. So you can do like more optimized things. I would say that's about it. But yeah, I guess it also depends on the use cases. But yeah, I'm not aware of many contracts that were written in pure YOL. But yeah, if you're using like a YOL, like inline assembly in Solidity, then I mean the obvious reason would be just to be optimizing very small portions, snippets of code. If you want to, yeah. So this is the test for the contract. That we just wrote, so still very simple, straightforward. We are also using the Huff deployer, and yeah, I added some console log just for the sake of it, but basically still quite straightforward. I'll just give you a few minutes if you want to write the test and try out. Oh, you had this? Oh, you don't need it. Yeah, obviously. Yeah, I'm a bit confused. Are you running the... Oh, but you are running the test from counter, and then you're checking maybe the other tests. Okay. All good? Yeah, just let me know if the tests are passing or if you're having any issues. How is it going? All good? It's oh, you added more things? Yeah. Nice. Okay, cool. All right. Yeah, that's. I don't have another contract after that, so if you want to, we can just be like talking if you have more questions, or if you want to, I don't know, add something else into the code and you want me to let you know how we could work, feel free to, yep.
มีคำถามออนไลน์บ้างไหมครับในออนไลน์มีขึ้นไหมอ๋อเนี่ยอ๋อมันเป็นของในห้องใช่ไหมงั้นก็เดี๋ยวก็จบละซีมา
What's the issue now? Failing. Assertion failed. Value. Increment value. What is doing increment? Yeah. Oh, okay, you want to, oh, I see, nice, okay, cool. So yeah, you're loading the cold data, then you're loading, yeah, it's good actually, it should be working, it's, yeah, yeah. To be honest, try adding like a return, I think that might be the issue, I'm not sure. Here we're not adding it. Yeah, I'm just. I think we might need it. Yeah, I'll copy paste the just return nothing just to see. This will return something. So just. So what you need, for example, if you put like 0, 0 return, it will just end the transaction. So you don't have to return something. You can just like put this to return a transaction, to stop the transaction. And if are you familiar with Foundry? Read. Okay. Oh, it works. Perfect. Okay, that was it. Nice. Okay, all good. Yeah, if the tests are failing, you might want to add here. I think it would be better, especially if you change the code. Here, you can do like you can add after that line return. So like this, but instead of having like 20 here, you can just like put 0, 0 return. So here you can just like return nothing. So this will just let know that. After calling this macro, then you just have to end the transaction. Because otherwise, what could happen is that set value is executed, and then you go here to the jump label, and then get value is executed also. So you have some weird scenarios. So I think it would be just better to do like add return here. Just return nothing. Just 0, 0 return. This should fix things. If you have this. Not working, try to do what I just said.
Yeah.
New function, just like return nothing.
Yeah.
Because it fixed the issue for the for him. Yep. Also,
another thing you can do is you can just do stop.
Yeah, stop also works, but I'm not sure about the gas cost.
You can just stop.
Yeah, you can stop also, but I'm not sure about the gas cost. We should check because sometimes stop is just like. Consuming the rest of the gas or things like that. So what? Yeah, you can just research and see like alt execution. Oh yeah, yeah. You can if you click here, you have more details. Yeah, successfully. Yeah, you can Yeah, it works. You can also add stop. Yeah, that's another way to just end the execution of the macro safely. Yeah, sure.
How does the function signal which set value you're referring to if you have multiple with different arguments? If you have multiple set value with taking different number of arguments?
Yeah, if you're like overloading, you mean? I think that's a good question. That's a good question. I need to check, to be honest. I have never done it in Huff, so I don't know, but that's I don't even know if it works actually. Let me check, but that's a good question. Yeah, I don't know. I don't have the answer now, but like 10 minutes left, 12 exactly, but yeah, I think maybe you had enough. As you want. If you have more questions, feel free to ask them. I will be happy to answer them if you want to cut like a few more minutes. But otherwise, well, I just want to say thank you guys for... I lost the clicker again. Thank you guys for attending this workshop. I was pretty excited to see many people, and I was happy to see that you guys were staying until the end and working and building the contracts and even adding more stuff. So that's pretty cool. So yeah, that's it. You can, if you are interested, you can follow Huff on Twitter. There's the website, there's the Discord. We are working on Huff 2. The new compiler is being re-written from scratch actually. We are going to be working also on the EOF support and many other things. So yeah, feel free to follow for more good stuff. Thank you guys.
Hello. Oh, it works. Nice to meet you. My name is Sasha. Today we will have a little presentation about Waku. It will be two presenters, me and Ivan. We will explain you overall problematics of peer-to-peer networks. We will go through common parts of peer-to-peer networks, challenges that are faced usually, and how they usually are dealt with, and the common trade-offs. Then we will explain a bit about Waku, which is a functionable peer-to-peer network that has some answers to some of the problems that will be mentioned. And we will show you some examples, and we will try to do a bit of programming. So, how are you guys familiar? Raise your hand if you are really familiar with peer-to-peer networks. You build one by yourself. You know ins and outs of libp2p or devp2p, or you build your stack. So maybe you can enjoy this talk, I hope, as well. But otherwise, it's more of an intermediate level. So let's start. So why do we even care about peer-to-peer networks? So first of all is that due to architectural decision of going with peer-to-peer, we guarantee some potential decentralization and censorship resistance that comes out of it. And why do we even want it? Is that because we are in crypto space, right? I think this is like something that does not need a lot of answers. But then usually this solution is made to introduce some degree of privacy and that data ownership. It's to provide this service to the users of our applications, networks, whatever. Other properties that peer-to-peer networks guarantee is that usually they are fault tolerant or resilient, and this comes out of the fact that we don't have single point usually there, and we can survive as a set of nodes if one, two, or even half of the nodes are offline or down. And then potentially we can get some scalability out of this decision. This is questionable actually, because peer-to-peer networks are known to be difficult to make right. But hypothetically, we can reach a high degree of scalability naturally. What challenges there are? So first one is that we need to build one and maintain ourselves. This is challenging because the peer-to-peer networks has a lot of complexity in it, like some set of protocols being implemented, so we need to make sure that all the peers understand each other, and then if we, let's say, release a new version of our software, we need to make sure that it somehow like gets propagated or something. This is quite challenging, as well as there is a lot of DevOps involved, like whenever we upgrade something, something might be down, then it impacts some other people. So it's difficult to do right. Reliability is also a big challenge in peer-to-peer networks. Why? Because it also depends on the degree of nodes, amount of nodes in the network. The less there are, the more reliable it is. So, like, if there is one node, it's quite reliable. If there are more, then it becomes challenging to make sure that all the protocols function correctly and the nodes propagate the messages in the right way. Then network discovery is a huge bottleneck there. All projects made different decisions there, but more or less there are some patterns that everyone follows. And security and traffic management. Like depending on the architecture of the peer-to-peer network we go with, we incur different pattern of how data will be propagated. So let's say for the case for Waku that later will be explained by my colleague Ivan, Waku goes with a gossip sub architecture, and it incurs some particular way of how message is going to be exchanged in the network. Other people might go with a mixnet or something else, so depends. And for the security, there are more parts than just encryption, that other people cannot read your data. There is also a security of overall network. How, like identity theft, like let's say if someone can pretend to be someone else in the peer-to-peer network, it's quite challenging and has to be addressed on a software level somehow. so we can use different algorithms here. The other problem there is that how to make the network not to go down because of like someone malicious there. Let's say if we have a peer that produces 90% of the traffic overall, right? We don't want a single node to consume all the resources of the network. Yeah, so this is a security question as well. How to build a peer-to-peer network? So these days there are a couple solutions. Usually everyone goes with CERT, do it yourself, DIY. And many projects just go there, try to figure it out. They figure it out somehow because all of us are quite good engineers, I hope. And all of them just answered the questions, just solved it, and release. They use just not for network stack, whatever is available in the language of their choice, and that's it. But other projects has figured out that it can be scaled somehow. So Dev P2P and Lib P2P got born. So they appeared approximately at the same time. Dev P2P is very dedicated for Ethereum stack, and it's like something that all Ethereum nodes implement. But there is also Lib P2P, which was more of a generic stack. Like it can be used by any project. It does not have any dependency on any blockchain whatsoever, and it's very modular. For Waku, it is the case that we built on top of Lib P2P, and we extended with our protocols. We continue building from there. So shared parts. It also somehow related to the challenges that I mentioned. And usually we care about peer discovery in the peer-to-peer networks, right? This is obvious. Unless we know our peers, we cannot form a network. And there are multiple choices that projects go with. Some of them are DNS discovery. We call some particular, we retrieve some DNS records. From there, we understand like this is a set of nodes that we can use, and we go on with them. Some choices might be like an exchange, further exchange. Like we ask the nodes if they know other nodes, right? So very natural way of discovering a network, same as humans behave. Then informational exchange. So a format, usually the networks try to converge into one format. So hence there is some specification for a package of data that is going to be populated throughout the network. Then something specific to the networking in the internet is that some peers might be hard to reach. So hence we need to use some hole punching techniques, which means that if I cannot dial you directly, maybe we can bypass it somehow, like you dial me instead. Or let's say if it is not possible, it's approximately I think 30% of the users overall, which is the case for some protocols. We may do relaying, which means that I am going to ask some other peer to relay you some data that I want you to see, and you do the same. So we like bypass this wall in between us. Then the other shared parts is that all the networks try to somehow secure themselves from DDoS. So hence some DDoS protections comes in play, and spam protection. How it can be addressed by different meanings. Usually it might be like some token exchange. There might be some common shared record of peers that are like reliable, whatever they can be used, can be trusted. So different ways. But one of the most difficult parts here is that it's hard to make it in a privacy-preserving way, so that we don't release some identity, or we don't even know who his peer actually is. And Waku has found some answer in partnership with other projects in the space. Other shared parts is that transports. So this one is very important because if our nodes in the network implement more transports, such as WebSocket secures, TCP, UDP, WebRTC, Web Transport. The more transport they implement, the more clients they can reach. Like let's say if we have a WebSocket implemented, we can be sure that our node can function not only between like some servers, right, but also with browsers. So hence we can serve more users. and much more. So there is a bandwidth management, like how to make sure that our nodes are very ecological in the resources that they have, the reputation, like we want to make sure that the peers which we are talking ad hoc right now are more or less fine or not. Encryption, this is a huge question as well, like we don't want the whole network know what we are talking about, what we exchange, right, and routing, more or less. So hence there are some trade-offs that we make while building the networks. And one of them is that do we want to have one huge network, or we want to have like some sub-networks that somehow talk to each other later on? I don't know. If we do some sharding, how many of them we want? Like 1, 2 groups, 3 groups, depending on the content exchanged maybe, right? So this is a conscious choice that we as developers have to make here. Then a message size, right? A data packet. The bigger it is, the slower propagation of it will be through the network, regardless of the architectural choice of it, right? So we want to be cautious of it, and we want to make the best choice for our particular need. And then rate limiting, right? We don't want anyone spam the network, consume all the resources. So which technology we use? Are we fine with having, let's say, a common ledger of trusted nodes, or we want to be more open, like publicly available networks that anyone can join? So in that case, what do we do? How do we address it? I don't know. It depends. Incentivization, right? So some of the projects, public networks, have no incentivization, but they still function well. And why it happens is that because people share a common cause. They want to be part of this network because it, let's say, gives some privacy. It gives underprivileged people access to internet without them fearing for any consequences or something, or just buying drugs, whoever, whatever. And discovery protocols, like there could be a different way of how we can discover. So we do some trade-offs here as well. Some can be slower, some can be faster. And what Waku does. So here I'm going to pass it down to Ivan, and he will tell you.
Thank you. Thanks. Hello, everyone. Okay, and in this part of the talk, we are going to overview the actual implementation of the Waku protocols. As my colleague mentioned, is an opinionated implementation of our view of how we consider is good to solve the well-known problems, such as the discovery, the problem of a NAT or a firewall, the problem of routing. This is covered by all of the protocols that are shown in this list. And aside from that, we introduced a new one, which is the RLN rate limiting one, and we are going to cover in a few seconds. Okay. Regarding discovery, we have 3 main discovery protocols. One is peer exchange. This is pretty centralized and is not ideal, but is useful in certain conditions. And what it does, sorry, what I'm explaining is not shown in the screen. But what peer exchange protocol does is it asks to other peer to share the peers that it knows, and it's just a request-response protocol where the other peer responds about the information of its peers. And then we have the DNS discovery, which is a very interesting protocol that is powered by DNS. And then we have the Discovery v5, which we consider to be more decentralized and more convenient for the Web3 scenario, and its based. Its implementation is based on Kademlia, and well, as you know, is the DHT. And what it does, it retrieves a random set of ENRs, and yeah, this is very intensively used in Waku. Okay, then regarding Another family of protocols that we have in Waku is the request response protocols, which are you will see in this talk that we have two main families of nodes. We have what we call a full node, which is basically a node that is part of the overlay of the network and produces the routing of the data. And then we have the edge nodes. And for these edge nodes, such as a mobile phone or a browser, it cannot participate in the routing protocol because it's data consuming. And for that reason, we created these request response protocols for helping, in order to help these edge nodes in different ways. For example, regarding the store node, its main purpose is to allow nodes to come when a node come back to participate in the network, to get back the latest state of the messages. Then we have the sync, and the main purpose of this protocol is to make sure that all the store nodes have the latest state and the same state of messages. Then we have light push. The purpose of this protocol is for edge clients to be able to participate in the network, to publish messages, and filter in the other way around. Okay, if we go further to the routing protocol. Oh, sorry. Anyway, okay. Okay, regarding the routing protocol, is we call it relay, and it's a kind of opinionated version of Gossip SAP, which is great and is very interesting. And we're going to cover very briefly how Gossip SAP works in this talk. Okay, this is a very simplified schema of pretty interconnected network, and the dots just represent nodes. And as you can see, all of the nodes, they are continuously exchanging control messages. Like, for example, the messages that I saw, the messages I'm interested in, and the control messages names are I want or I need. No, and then we have the Waku messages. That these are the actual messages that transport data in the network. Something important to bear in mind is that we can have, for example, 100 connections to 100 nodes, but one single node will spread data, Waku messages, to up to 6-8 nodes maximum, and every node will pick up the best from its neighbors, will pick up the best nodes regarding according to certain parameters, such as latency, number of messages per second, how responsive a node is, and so on. And okay, and how does it work? Every node has a heartbeat that happens every second, and on every second, every node measures or gives a certain score to all of its neighbors, and according to this score, if the score is too low, then it ignores the node. It doesn't mean it completely disconnects to the node. It keeps gossiping, asking what messages do you have, what I have, etc. But it doesn't participate or interact, sharing important data, no? And it only establishes a mesh with amplification factor of a value between 4 or 8. This is how we are configuring at the moment, and yeah. And in this slide, it's just a simple example of how a single node establishes at certain point in time what is the about its neighbors, what is the peer score, and for example, if node A receives a message, then given that the overlay network is established with B and D, it will only deploy or spread the message to B and D, and not others. And something important to bear in mind is that this can change every second. It's not a fixed overlay network, but it's something that is alive. Okay, and then we have the rate limit nullifier. This is a very interesting topic and very interesting technology because it allows to protect the network against spam in a private way, so that the node can prove that it belongs to the network without actually disclosing its information, or it's very cool how it's implemented. And it's based on CK-SNARK technology. And we keep a smart contract currently in Sepolia, where the membership set is configured. I think we are about to release version 2 of RLN. And yeah, it's basically this is a quite complex topic, and it's beyond my knowledge. But just to get an idea, the main purpose of it is to protect the network against spam in a private way. Okay, regarding the Waku message, as you remember, this is the one that is being sent across the overlay network. Basically, it contains a bit more fields than shown in the left, but basically we have a payload for which we don't impose any additional encryption. We leave the encryption to the app developers. And regarding encryption, it's important something to notice that there is point-to-point encryption inherited by the libp2p, which is made following the noise protocol. And we have the content topic, which is a field useful from for example, in the filter protocol. An edge node subscribes to a certain content topic, and from all the information that is shared across the network, the messages the edge node is interested in is going to be sent to them. Okay. And regarding this point.
Okay, so to build on top of Waku, I'm just gonna introduce you a bit to CDKs that we have and languages we support. So this QR code leads you to documentation website. There is a lot of information, links to our communities and such. If you have any questions about anything like Waku related, code is failing, behaves unexpectedly, reach out to us. Everything is there. But we do support JavaScript and TypeScript right now, and NIM is and second language that it's more of a first language, but still, it's the language of our choice, and we have an implementation of Waku in NIM language, and it's compilable to C, and you have the C artifact that you can consume later on. We're also working on better Go bindings and CDK and Rust and Python. They are work in progress, but can be used to some cases right now. So for JS Vacu, we have like a couple of packages. Main one is Vacu SDK. Just install it, use it. It's going to work. I hope so. Then we have a wrapping for React. Also deals with React lifecycle methods and stuff that busts a lot of creates a lot of unexpected behavior. Then we have a create app that can bootstrap your application quite easily. Might be useful as well. So the main users right now are Status. Status is a messaging application which is dedicated for one-to-one chat as well as communities, and it uses Vacu underneath. It has its own set of nodes that are operating. There are a bit different guarantees than defaults that we propose projects to use, such as a bit extended store retention, right? Because such applications want to retain data longer. Then a second project that uses Vacu is Railgun. This is privacy-oriented DeFi project, and Vacu is used for broadcasting fees in the network so that it's not known where it originates from. Then the Graph also uses Vacu for information exchange between some of their nodes. Yeah, so and use cases, there can be anything, such as DeFi, as I already mentioned, community-run apps as well, some social interactions, wallet-to-wallet communication, gaming, you name it. So we saw interesting applications even with geolocation positions, such as users' geolocation gets mapped to a particular namespace in Vacu network, and then you can talk to the room in which you are located. Quite interesting approach to create a layer on top of reality. So today we're going to show you some of the examples. This link will lead you to a repository with our examples where we experiment, where we play around, and as well as do something for users. I will show you an application named Bodybook. We created it as a POC just to show people around here at Devcon. And there will be more examples, and we can try to do some programming if you are interested. Otherwise, I will just walk you through some simple one-page JavaScript application with request-response protocols that are used. Do you have any questions at this point? Maybe we can do a quick Q&A before we go into some code presentation. Oh, yeah, there is a question. Sorry.
Specific for native mobile SDK?
So do we have a mobile
like in
SDK?
Java or Kotlin or Swift? On your plans, I mean.
Not now. We have it in plans, yes. JavaScript version can be used in React Native. We did some bindings. We didn't prove it working reliably, so this is also work in progress. We had some Go Vacu being adapted for running is also in React Native or other stuff, but also Status is using Vacu as well, but they did a little bit more work than just installing it. So it is work in progress. Yes.
So
please.
Is there a public network that the Vacu nodes run on, or are you expected to run your own nodes for the applications that you run?
Yeah, so the main difference between Vacu and, let's say, libp2p, as I mentioned, libp2p is a stack that we are using, and anyone can, let's say, me, you, we together want to build a network, we create an application out of libp2p, right? What Vacu does differently is that it provides a set of protocols, like solutions to some problems that we observe and we want users to have dealt with, as well as we have a running network, which is called the Vacu network, TWN, and I will show you how to join it, let's say, from JavaScript CDK in a couple of lines of code, and you can hook in your own nodes to it, or use it as a signaling node, let's say, to create your own subnetwork or something like that. Yes. Any more? Okay, so I'm gonna go to my laptop and let's see what we can do with the code today. So this one is for example with Rust. It uses a NIM version of Waku, some bindings, and you can scan it and see how it is implemented. Later on, Ivan will go and present himself the code and walk you through it. So bodybook, if you scan, this will lead you to the source code of the simple one-page application. Otherwise, you can visit bodybook.fun. And what it does is that once you open it, you can create a book. And then later on at the conference or somewhere, you can come to people and ask them to sign your book, like collect signatures. These signatures will be created from a wallet, right? So let's say a MetaMask wallet or something. And the interesting point about this application is that the signatures will be exchanged through Waku, and they won't be committed to the blockchain. Hence, there will be like an easy propagation of this information, and it will be stored in the store protocols that Ivan mentioned about. So here we have like a couple of just books, whatever, and there are some signatures attached. Yeah, so if you create it, it's gonna appear here, and yeah, so this is very simplistic application, but still very interesting use case. Yeah, okay, so then you can run a node. This is another application example of how Waku can be used. You can be just a node operator, so contributing to the network. Let's say if you have a spare Raspberry Pi 4 gigs of RAM or something, just opening a Docker and doing one line can already contribute to the network quite a bit. Though I'm lying, it's not one line, it's more of one line to run in your terminal. And now if you open this link, it will show you a basic JavaScript application. It will lead you to the code, which I will go and show now. I hope you see it well. Yeah? Is it readable? Should I increase it a bit? Okay, a bit. This is just single one file application which consumes JavaScript CDK. And you have to create an instance of a node first, right? So hence this create light node function is used. It accepts like different parameters. There you can pass particular coordinates of the network that you want to use if not a default network is in use. So by default network, I mean here TWN. And if we want to use a default set of configuration, we just pass default bootstrap. Other thing that Waku has in it is the message, the data packet, right? It gets propagated through the network, and there are some properties of this data packet that help to do routing. And one of them is content topic, and content topic should be perceived as the namespace under which data should be exchanged from the perspective of an application. So let's say if I'm in an application like Telegram, right? A content topic can be one chat, one group in which the messages are getting exchanged. So hence, I am, as a user, have a set of chats, and only from them I want to receive messages. If they are coming from different chats, I don't want to receive them. That's the simple idea here. So, and as anything in the computer science, we want to create a reader and writer. We have a blob of bytes being exchanged in the network, and these two lines are doing exactly this. They create decoder and encoder, and they are configured to be using one particular content topic. Later on, we have to start the node just to initiate the process as part of API. And the second line does an important part, is that we block execution of application until we receive some peers. This is just one way to do it. Another way might be to not to do it and rely on lazy connection that will be managed by GS Waku in that case. So then here I'm going to show two protocols through two lightweight protocols that we have for edge nodes, as Ivan mentioned. One of them is filter and another one is light push. They come complementary. And for filter, the main use case is that you want to receive only those messages that you are interested in without consuming a lot of bandwidth, etc. And filter exactly does the same. We send a request to a service node and we ask it to later return a messages to us. The whole interaction happens over WebSockets as of now. In future, we might go into having a web transport, which is work in progress right now, as well as WebRTC might be in use for some cases. But regardless of it, we rely on the service node to return us messages in that case. We can do a lot of heuristics. As I mentioned, peer-to-peer networks are not ideal. Some of these problematic parts are having unreliable nodes. One node can pretend to be reliable by advertising itself with some protocols that we are interested in, but it might not do what we want. What we do in that case, we implement some heuristics inside, such as if I sent a message and I didn't receive it back from that node, it's probably not reliable, I'm going to drop it. So this is a part of overall umbrella term reliability, which we were working for the past 6 months. So yeah, this is a simple callback from JavaScript perspective, nothing fancy. As to pass data inside, we just, wait push. So here, just one for loop, sending 10 messages from our side. The send is exactly send. It's just one request over existing transport. In our case, again, it's WebSockets. It just creates a blob of bytes and sends it. Yeah, so let's see it in action. Okay, so I'm going to open localhost. I have it open, and yeah, there are two tabs. Here we want to reconnect. Here we want to reconnect as well. To do, we are waiting for peers. No peers available. Something happened. Good. Here we subscribed and here we subscribed. So now we are sending some messages in the loop and we are receiving some messages. As we see, one of the properties of the network is that how Waku functions is that we're going to receive our own messages, and this can be quite useful for some of the applications. Yeah, so this does its thing, so it works. One of the interesting things is that there are a lot of logs, error logs. They're expected as for they cannot be ignored. Are there any questions right now? Yeah, please. Can you repeat to, yes?
Yeah, the light node instance, it's not a P2P instance.
No, actually it is. So, but it depends, right? There are some trade-offs that we have to make in the browser. One of them is that a set of available transports for the browser tab, right? Browser is a very restricted environment. There are a lot of things that we cannot do, such as we cannot do a TCP connection directly or UDP connection directly. We have to do either HTTP or a WebSocket connection. That's it. WebRTC as well, but there are limits, right? So, and also resources. Browser is very limited in how much computation we can do, like heavy computation, right? The browser tab can become suspended quite easily by operational system. Everything stops working in there, right? And it cannot be a fully functional part of the network. Hence, we call it an edge node, meaning that the traffic kind of ends there, right? It does not participate as a full node, it's not full. But it is peer-to-peer in the meaning that the browser tab is independent in how it discovers the network. It uses almost everything but discovery Wi-Fi that Ivan mentioned. It discovers the network through DNS and peer exchange, And as for our case, right now we have 24 peers. So right now we have 24 WebSocket connections to 24 full nodes that we can use interchangeably or in rotation, or if we observe that some does not work, we can use others. And if others does not work, we can do something else. And also the peer exchange is an ambient peer discovery, meaning that it happens always in the background. So, and we can see that we have quite a few nodes collected right now. Right now, 25. But the longer the browser tab will be executing, will be open, the more peers we're gonna discover and use eventually. So from that regard, it is peer-to-peer, and it owns its own stack as to like encryption. Yeah.
So this provides like a WebSocket server. So all these nodes provide a separate WebSocket server for these edge nodes?
Yeah, exactly. This is very interesting because we can reason about it as to having a serverless application. We don't have kind of server, but we still can have a connection in between them, right? It's backendless. Yes.
And I mean, one thing from the previous slide I have was the syncing, right? So how does the syncing works? Because you said you only send messages to like 4 or 5 peers at a time. So how does it know like the message?
Yeah, so how does the node knows where to send the messages? Yes, was that the question? Yes, so Gossip Sub is not a directed way of routing the traffic, and we rely here on eventual consistency, let's name it like that. We know that the node will relay messages to its peers. In our case, it's 4, 5, 8, something like that, right? And we know that all the peers kind of connected to each other, right? We have it as a graph. So if someone originates with a message on one end, by the rules of Gossip Sub, it's going to propagate till the other end. But it can take a lot of time as well as little to time, right? We don't know where the node is placed in the network. And I don't mean geographical position, but like logical from the Vacu standpoint. Yeah, so in our simulations, we had simulations like up to 10,000 nodes. And we had the numbers as to, in average, from 200 to 500 milliseconds was the message propagation. In current TWN, which supports RLN as for the meaning to shield from the DOS, we have like 1,000 nodes, and the message propagates quite fast. Yeah.
And so if the node is offline and comes in, right, does it get the older messages that were broadcast?
Yeah, this is why we actually came up with store protocol, right? In peer-to-peer networks, we kind of think about the transport, right? These are nodes, they talk to each other. A store, everything else is like application logic. We agree with that, right? At each application that uses, let's say, Vacu stack or the network needs to implement its own stuff on top, a store including. But we still understand there is a need to have a short-lived, like while I'm offline, let's say for 1 hour, right? I still want to get back these messages. So store is for full nodes, and it's going, once, let's say your full node goes offline and goes online back, it's just going to ask the peers around for the missing messages through the store protocol, and it's going to do the thing. Thank you. Any more questions? No? Let's see something with Rust been done, and if you want, we can do some programming or something.
Okay, thanks, Sasha. Okay, in this part of the session, we're going. Is it visible? We're going to cover a few examples regarding the Waku Rust bindings. By the way, credits to Richard for the great job in this repo. And this is the in there. Well, in QR shared earlier on by Sasha. You will get a branch to do this where this is implemented. And let's first of all overview the repo and what we have in there. Basically, we have Waku SEAs, bindings, and the examples. And in Waku SEAs, this is the one that implements the NWaku. This is the NIM implementation. And from here, we've created, or we are working on the creation of C library that exposes all the functionality that is available from a Waku node, the discovery, the creation of a node, connection to another peer, hole punching, etc. All the libp2p protocols that we've mentioned earlier on are covered by the NIM implementation. And in this C library, what we are doing is we are exposing these features through FFI to any other languages. At the moment, as Sasha mentioned, we are covering Golang, Rust, Python, C++, and Node.js. Okay, let's carry on in this particular case. Then we have the Waku bindings crate, and what it does is a lib crate, which is just a wrapper around the Waku SEAs. And in there we have the implementation of the bindings stuff, and all the complexity is tackled within this module. And yeah, you will see that we apply a technique called trampoline, and that helps us to interact with Rust. With the libwaku library from Rust. And then we have in this particular case, we have a few consumers, and this is just a simple application. Well, it uses Tokyo as a sync framework, and what it does, it basically at first it creates a Waku node with certain parameters. Then it establishes the DNS discovery URL. This is for retrieving the bootstrap nodes. In order for the node to start participating in the network, it needs an initial help. And for that reason, we have this. And from there, many other nodes can be inferred. And then we start this discovery v5 protocol, which is in charge of discovering other nodes in a decentralized way. Okay, this is part of the example of this application. Maybe the example is not super idiomatic in terms of Rust at the moment, but it's just a proof of concept to see how a Waku node can be integrated in Rust. And in this particular case, the main purpose of the application, or what the Waku node is used in this case, is just for sharing the game state across users, across the players. Okay, and given that we have a user interface and something important to bear in mind is that the the incoming messages by the node. These messages are being handled by the libwaku, which is implemented in NIM. And something important to mention is that this Waku node is running in a separate thread, and we need to, and the libwaku establishes a communication with this thread. This is needed because the NIM runtime should run separately from any other runtime, such as the Rust, Golang, Node.js, etc., in order to make it work properly. Because as we are using nowadays NIM, we are using it with a garbage collector, and it needs to run on its own thread. And something I wanted to mention is that all the incoming messages, they come in this closure. In here, as the example is implemented now, it starts the Waku node, and then we pass. We subscribe the node to a certain topic, just the game topic, and we pass a closure, which is in charge of getting the incoming messages. And with this, what we are doing is we are notifying the main thread about the incoming message, so that the game state can be updated when new. And now let's do a small demo. In this case, just we have two instances of the tic-tac-toe application. On the left, each of them is running a Waku node. Then we say this is going to play as X, and this is going to play as O. Then they can play, and well, it's a very simple example. In this case, player X won. And okay, something else I wanted to share is in this presentation. Sorry. Feel free to clone this example because we are going to play a little bit with it. It's just you will find it in the same Waku Rust bindings repo, and it's a bit more simpler. And what it does, it creates is more or less the same, but more simplified. It creates a Waku node. We are passing shards. This is the shard thing is something that is needed to split traffic in a certain way. It can be understood as a way of channels or communication channels in Gossip's app. Then we are establishing maximum of 1 megabyte log level. Content topics. Sorry, no. This is the pub subtopic. We set the keep alive to true, and as we saw earlier on, we enable the DNS discovery and disk v5. Okay, and in this case, after that, after creating the node, we just start it. And then we establish, we subscribe to the Waku, to the topic, and that's it. And in this example, it just creates a node, starts it, subscribes to the topic, and just wait until a Control C is pressed. And if we run it, we will see that these logs are coming from the implementation of NIM Wago. Yeah. Okay, and as you can see, the node is starting to receive relay messages because it's subscribed to. And yeah, and that's it. And we are receiving messages from the network. I believe they come from status because I connected to the status network, and well, just that's it. I don't know if there are questions or comments, or would you like to see something else, or?
How is the DHT look for the network? Like, what flavor of DHT?
How is the DHT lookup being done? Or you mean? Yeah, we have a Discovery 5 client, and it performs a request to the network, and it's.
But so, like, how does it decide where to route the message? Just on the peer scoring, or what?
You mean yeah, exactly. The messages are being routed by a healthy mesh. If there are peers that are misbehaving or are spamming the network, then they are blocked and they don't participate in the network. Okay. In that case, if no more question, thank you so. Yes. Yeah, thank you for the question. Good question indeed. As Sasha mentioned, the gossip sub itself, it doesn't guarantee a certain message to reach a certain point, and for that reason, we are working on implementing what we call reliability protocols, and somehow we add an additional layer of redundancy. And there is sorry, I forgot the precise name, but one previous implementation of, or one enhancement is to consider that one message has been received properly if it has been received by a store node. So we somehow we use the store node as a leverage to reinforce the transmission of a message. But yeah, indeed, this is a very big problem that we need to overcome, and yeah, we are working on it. And thank you. Thank you. Any other question? Okay, in that case, thank you so much for the time, and see you around.
you.